This is CS50, and this is week 2. Now that you have some programming experience under your belt in this more arcane language called C, among our goals today is to help you understand exactly what you have been doing these past several days wrestling with your first programs in C so that you have more of a bottom-up understanding of what some of these commands do and ultimately what more we can do with this language. So this, recall, was the very first program I wrote in this language called C, much more textual certainly than the Scratch equivalent. But at the end of the day, computers, your Mac, your PC, VS Code doesn't understand this actual code. What's the format into which we need to get any program that we write? Just to recap. So binary, otherwise known as machine code, right? The zeros and ones that your computer actually does understand. So somehow we need to get to this format, and up until now we've been using this command called make, which is sort of aptly named because it lets you make programs, and the invocation of that has been pretty simple. Make hello sort of looks in your current directory or folder for a file called hello.c implicitly, and then it compiles that into a file called hello, which itself is executable, which just means runnable, so that you can then do /hello. But it turns out that make is actually not a compiler itself. It does help you make programs, but make is this sort of utility that comes on a lot of systems that makes it easier to actually compile code by using an actual compiler, the program that converts source code to machine code on your own Mac or PC or whatever cloud environment you might be using. In fact, what make is doing for us is actually running a command automatically known as clang for C language. And so in fact here, for instance, in VS Code is that very first program again, this time in the context of a text editor, and I could compile this with make hello, but let me go ahead and use the compiler itself manually, and we'll see in a moment why we've been automating the process with make. I'm going to run clang instead, and then I'm going to run hello.c. So it's a little different how the compiler's used. It needs to know explicitly what the file is called. I'll go ahead and run clang hello.c, enter. Nothing seems to happen, which generally speaking is a good thing because no errors have popped up. And if I do ls now for list, you'll see there is not a file called hello, but there is a curiously named file called a.out. This is a historical convention, stands for a similar output, and this is just the default file name for a program that you might compile yourself manually using clang itself. Let me go ahead now though and point out that that's kind of a stupid name for a program, even though it works. /a.out would work, but if you actually want to customize the name of your program, we could just resort to make, or we could do explicitly what make is doing for us, because it turns out some programs among them make support what are called command line arguments, and more on those later today. But these are like literally words or numbers that you type at your prompt after the name of a program that just influences its behavior in some way. It modifies its behavior. And it turns out if you read the documentation for clang, you can actually pass a -o for output command line argument that lets you specify explicitly what do you want your outputted program to be called, and then you go ahead and type the name of the file that you actually want to compile from source code to machine code. Let me go ahead and hit enter now. Again, nothing seems to happen, and I type ls and voila. Now we still have the old a.out because I didn't delete it yet, and I do have hello now, so /hello voila runs hello world again. And let me go ahead and remove this file. I could of course resort to using the explorer on the left hand side, which I'm going to have it closing just to give us more room to see, but I could go ahead and right click or control click on a.out if I want to get rid of it, or again, let me focus on the command line interface, and I can use, anyone recall, we didn't really use it much, but what command removes a file? rm. So rm for remove, rm, a.out, enter, remove regular file, a.out, y for yes, enter, and now if I do ls again, voila, it's gone. All right, so let's now enhance this program to do the second version we ever did, which was to also include CS50.h, so that we have access to functions like getString and the like. And let me go ahead and do string name getString, what's your name, question mark. And now let me go ahead and say hello to that name with our %s placeholder, comma name. So this was version 2 of our program last time that very easily compiled with make hello. But notice the difference now. If I want to compile this thing myself with clang using that same lesson learned, all right, let's do it. Clang -o hello, just so I get a better name for the program, hello.c. Enter. And a new error pops up that some of you might have encountered on your own. So it's a bit arcane here, and there's this mention of a cryptic-looking path with temp for temporary there, but somehow my issue's in main, as we can see here. It somehow relates to hello.c, even though we might not have seen this language last time in class, but there's an undefined reference to getString, as though getString doesn't exist. Now your first instinct might be, well, maybe I forgot CS50.h, but of course I didn't. That's the very first line of my program. But it turns out make is doing something else for us all this time. Just putting CS50.h, or any header file at the top of your code for that matter, just teaches the compiler that a function will exist. It sort of asks the compiler to trust that I will eventually get around to implementing functions like getString and CS50.h and standard.io.h, like printf therein. But this error here, some kind of linker command, relates to the fact that there's a separate process for actually finding the zeros and ones that CS50 compiled long ago for you, that the authors of this operating system compiled for you long ago in the form of printf. We need to somehow tell the compiler that we need to link in code that someone else wrote, the actual machine code that someone else wrote and then compiled. So to do that, you have to type -l CS50, for instance, at the end of the command. So additionally telling clang that not only do you want to output a file called hello and you want to compile a file called hello.c, you also want to quote unquote link in a bunch of zeros and ones that collectively implement getString and printf. So now if I hit enter, this time it compiled OK, and now if I run /hello, it works as it did last week, just like that. But honestly, this is just going to get really tedious really quickly. Notice already, just to compile my code, I have to run clang -o hello hello.c -l CS50, and you're going to have to type more things too. If you want to use the math library, like to use that round function, you would also have to do -lm typically to specify give me the math bits that someone else compiled, and the commands just get longer and longer. So moving forward, we won't have to resort to running clang itself, but clang is indeed the compiler. That is the program that converts from source code to machine code, but we'll continue to use make because it just automates that process. And the commands are only going to get more cryptic, the more sophisticated and more featureful your programs get, and make, again, is just a tool that makes all that happen, so to speak. Let me pause there to see if there's any questions before then we take a look further under the hood. Yeah, in front. Sure, let me come back to that in a moment. What does the -l CS50 mean? We'll come back to that visually in just a moment. But it means to link in the zeros and ones that collectively implement getString and printf. We'll see that visually in a sec. Yeah, behind you. Really good question. How come I didn't have to link in standard.io? Because I used printf in version 1. Standard.io is just literally so standard that it's built in. It just works for free. CS50, of course, is not. It did not come with the language C or the compiler. We ourselves wrote it. And other libraries, even though they might come with the language C, they might not be enabled by default, generally for efficiency purposes. So you're not loading more zeros and ones into the computer's memory than you need to. So standard.io is special, if you will. Other questions? Yeah. Oh, what does the -o mean? So -o is shorthand for the English word output. And so -o is telling clang to please output a file called hello, because the next thing I wrote after the command line recall was clang -o hello, then the name of the file, then -l CS50. And this is where these commands do get and stay fairly arcane. It's just through muscle memory and practice that you'll start to remember, oh, what are the other commands that what are the command line arguments you can provide to programs? But we've seen this before. Technically, when you run make hello, the program is called make. Hello is the command line argument. It's an input to the make function, albeit typed at the prompt, that tells make what you want to make. Even when I used rm a moment ago and did rm of a.out, the command line argument there was called a.out, and it's just telling rm what to delete. It is entirely dependent on the programs to decide what their conventions are, whether you use -this or -that, but we'll see over time which ones actually matter in practice. So to come back to the first question about what actually is happening there, let's consider the code more closely up. So here's that first version of the code again with standard.io.h and only printf, so no CS50 stuff yet, until we add it back in and have the second version where we actually get the human's name. When you run this command then, there's actually a few things that are happening underneath the hood, and we won't dwell on these kinds of details. Indeed, we'll abstract it away, so to speak, by using make, but it's worth understanding, at least from the get-go, how much automation is going on so that when you run these commands, it's not magic. You actually do have this bottom-up understanding of what's going on. So when we say you've been compiling your code with make, it's a bit of an oversimplification. Technically, every time you compile your code, you're having the computer actually do 4 distinct things for you. And this is not 4 distinct things that you need to sort of memorize and remember every time you run your program what's happening, but it helps to sort of break it down into building blocks as to how we're getting from source code, like C, into zeros and ones. It turns out that when you compile quote-unquote your code, technically speaking, you're doing 4 things sort of automatically and all at once. Pre-processing it, compiling it, assembling it, and linking it. Just humans decided, let's just call the whole process compiling. But for a moment, let's just consider what these steps are. So pre-processing refers to this. If we look at our source code here, version 2, that uses the CS50 library and therefore getString, notice that we indeed have these include lines at top, and they're kind of special versus all the other code we've written because they start with hash symbols specifically. And that's sort of a special syntax that means that these are technically called preprocessor directives. A fancy way of saying they're handled special versus the rest of your code. In fact, if we focus on CS50.h, recall from last week that I provided a hint as to what's actually in CS50.h, among other things. Like what was the one salient thing that I said was in CS50.h, and therefore why we were including it in the first place. So getString, specifically the prototype for getString. We haven't made many of our own functions yet, but recall that anytime we've made our own functions and we've written them like below main in a file, we've also had to somewhat stupidly copy-paste the prototype of the function at the top of the file just to teach the compiler that this function doesn't exist yet. It does down there, but it will exist. Just trust me. So again, that's what these prototypes are doing for us. So therefore, in my code, if I want to use a function like getString or printf for that matter, they're not implemented clearly in the same file. They're implemented elsewhere. So I need to tell the compiler to trust me that they're implemented somewhere else. And so technically, inside of CS50.h, which is installed somewhere in the cloud's hard drive, so to speak, that you all are accessing via VS Code, there's a line that looks like this. A prototype for the getString function that says the name of the function is getString. It takes one input or argument called prompt, and that type of that prompt is a string. getString, not surprisingly, has a return value, and it returns a string. So literally that line and a bunch of others are in CS50.h, and so rather than you all having to copy-paste the prototype, you can just trust that CS50 figured out what it is. You can include CS50.h, and the compiler is going to go find that prototype for you. Same thing in standard.io. Someone else. What must clearly be in standard.io.h, among other stuff, that motivates our including standard.io.h too? Yeah. Printf, the prototype for printf, and indeed, I'll just change it here in yellow to be the same. And it turns out the format, the prototype for printf is actually pretty fancy because, as you might have noticed, printf can take 1 argument, just something to print, 2 if you want to plug a value into it, 3 or more. So the ... just represents exactly that. It's not quite as simple a prototype as getString, but more on that another time. So what does it mean to pre-process your code? The very first thing the compiler, Clang in this case, is doing for you when it reads your code top to bottom, left to right, is it notices, ooh, here is hash include. Oh, here's another hash include. And it essentially finds those files on the hard drive, CS50.h, standard.io.h, and does the equivalent of copying and pasting them automatically into your code at the very top, thereby teaching the compiler that getString and printf will eventually exist somewhere. So that's the pre-processing step, whereby, again, it's just doing a find and replace of anything that starts with hash include. It's plugging in the files there so that you essentially get all the prototypes you need automatically. OK, what does it mean then to compile the results? Because at this point in the story, your code now looks like this in the computer's memory. It doesn't change your file. It's doing all of this in the computer's memory or RAM for you, but it essentially looks like this. Well, the next step is what's technically really compiling, even though, again, we use compile as an umbrella term. Compiling code in C means to take code that now looks like this in the computer's memory and turn it into something that looks like this, which is way more cryptic. But it was just a few decades ago that if you were taking a class like CS50 in its earlier form, we wouldn't be using C if it didn't exist yet. We would actually be using this, something called assembly language. And there's different types of or flavors of assembly language, but this is about as low level as you can get to what a computer really understands, be it a Mac or a PC or a phone, before you start getting into actual zeros and ones. And most of this is cryptic. I couldn't really tell you what this is doing unless I really thought it through carefully and rewound mentally years ago from having studied it, but let's highlight a few keywords in yellow. Notice that this assembly language that the computer is outputting for you automatically still has mention of main, and it has mention of getString, and it has mention of printf. So there's some relationship to the C code we saw a moment ago. And then if I highlight these other things, these are what are called computer instructions. At the end of the day, your Mac, your PC, your phone actually only understands very basic instructions like addition, subtraction, division, multiplication, move into memory, load from memory, print something to the screen, like very basic operations. And that's what you're seeing here. These assembly instructions are what the computer actually feeds into the brains of the computer, the CPU, the central processing unit, and it's that Intel CPU or whatever you have that understands this instruction and this one and this one and this one, and collectively, long story short, all they do is print hello world on the screen, but in a way that the machine understands how to do. So let me pause here. Are there any questions on what we mean by pre-processing, which just finds and replaces the hash includes symbols, among others, and compiling, which technically takes your source code once pre-processed and converts it to that stuff called assembly language? Correct. Each type of CPU has its own instruction set. Indeed. And as a teaser, this is why, at least back in the day when we used to install software from CD-ROMs or some other type of media, this is why you can't take a program that was sold for a Windows computer and run it on a Mac or vice versa, because the commands, the instructions that those two products understand are actually different. Now, Microsoft or any company could generally write code in one language like C or another, and they can compile it twice, saving a PC version and saving a Mac version. It's twice as much work, and sometimes you get into some incompatibilities, but that's why these steps are somewhat distinct. You can now use the same code and support even different platforms or systems if you want. All right, assembling. Thankfully, this part is fairly straightforward, at least in concept, to assemble code, which is step 3 of 4, that is just happening literally for you every time you run make or in turn Clang. This assembly language, which the computer generated automatically for you from your source code, is turned into zeros and ones. So that's the step. That last week I simplified and said when you compile your code, you convert it to source code, from source code to machine code. Technically, that happens when you assemble your code, but no one in normal conversations says that. They just say compile for all of these terms. All right, so that's assembling. There's one final step. Even in this simple program of getting a user's name and then plugging it into printf, I'm using 3 different people's code, if you will. My own, which is in hello.c, some of CS50's, which is apparently in hello.c, which is in CS50.c, which is not a file I've mentioned yet, but it stands to reason that if there's a CS50.h that has prototypes, turns out the actual implementation of getString and other things are in CS50.c, and there's a third file somewhere on the hard drive, so to speak, that's involved in compiling even this simple program. Hello.c, CS50.c, and by that logic, what might the other be? Yeah. standard.io.c. And that's a bit of a white lie because that's such a big fancy library that there's actually multiple files that compose it, but the same idea, and we'll take the simplification. So when I have this code now, and I compile my code here, I get those zeros and ones that end up taking hello.c and turning it effectively into zeros and ones that are combined with CS50.c, followed by standard.io.c as well. So let me rewind here. Here might be the zeros and ones for my code, the 2 lines of code essentially that I wrote. Here might be the zeros and ones for what CS50 wrote some years ago in CS50.c. Here might be the zeros and ones that someone wrote for standard.io decades ago. The last and final step is that linking command that links all of these zeros and ones together, essentially stitches them together into one single file called hello, or called a.out, whatever you name it. That last step is what combines all of these different programmers' zeros and ones. And my God, like now we're really in the weeds. Who wants to even think about running code at this level? You shouldn't need to, but it's not magic. When you're running make, there's just some very concrete steps that are happening that humans have developed over the years, over the decades, that sort of break down this big problem of source code going to zeros and ones, or machine code, into these very specific steps. But henceforth, you can call all of this compiling. Questions or confusion? Yeah? Sure, what does a.out signify? A.out is just the conventional default file name for any program that you compile directly with a compiler like Clang. It's just kind of a meaningless name, though. It stands for assembler output, and assembler might now sound familiar from this assembling process. It's just kind of a lame name for a computer program, and so we can override it by outputting something like hello instead. Yeah? So to recap, there are other prototypes in those files, CS50.h, standard.io.h. Technically, they're all included at the top of your file, even though you, strictly speaking, don't need most of them. But indeed, they are there, just in case you might want them. And finally, any other questions? Yeah? Doesn't matter what order we're telling the computer to run. Sometimes with libraries, yes, it matters what order they are linked in together. But for our purposes, it's really not going to matter. It's just make is going to take care of automating that process for us. All right, so with that said, henceforth, compiling technically is these 4 things, but we'll focus on it just as a higher level concept, an abstraction, if you will, known as compiling itself. So another process that we'll now begin to focus on a little more this week, because invariably this past week you ran up against some challenges. You probably created your very first bugs or mistakes in a program. And so let's focus for a moment on actual techniques for debugging. As you spend more time this semester, in the years to come, if you continue to program, you're never, frankly, probably going to write bug-free code ultimately. Your programs are just going to get more featureful, more sophisticated, and we're all just going to start to make more sophisticated mistakes. And to this day, I write buggy code all the time, and I'm always horrified when I do it up here, but hopefully that won't happen too often. But when it does, it's just a process now of debugging, trying to find the mistakes in your program. And you don't have to just stare at your code or sort of shake your fist at your code. There are actual tools that real-world programmers use to help debug their code and find these faults. So what are some of the techniques and tools that folks use? Well, as an aside, if you've ever bugging a program is a mistake, that's actually been around for some time. If you've ever heard this tale, some 50+ years ago, in 1947, this is actually an entry in a logbook written by a famous computer scientist named Grace Hopper, who happened to be the one to record the very first discovery of a quote-unquote actual bug in a computer. This is actually like a moth that had flown into, at the time, what was a very sophisticated system known as the Harvard Mark II computer, sort of very large, sort of refrigerator-sized type systems, in which an actual bug caused an issue. The etymology of bug, though, actually predates this particular instance, but here you have, as any computer scientist might know, the example of the first physical bug in a computer. How, though, do you go about removing such a thing? Well, let's consider a very simple scenario from last time, for instance, when we were trying to print out various aspects of Mario, like this column of 3 bricks. Let's consider how I might go about implementing a program like this. And let me switch back over to VS Code here, and I'm going to go ahead and write a program. And I'm not going to trust myself, so I'm going to call it buggy.c from the get-go, knowing that I'm going to mess something up. But I'm going to go ahead and include standard.io.h, and I'm going to go ahead and define main as usual. So hopefully no mistakes just yet. And now I want to print those 3 bricks on the screen using just hashes for bricks. So how about for int I gets 0, I less than or equal to 3, I plus plus. Now inside of my curly braces, I'm going to go ahead and print out a hash followed by a \n, semicolon. All right, saving the file, doing make buggy, enter, it compiles. So there's no syntactical errors. Like my code is syntactically correct, but some of you have probably seen the logical error already, because when I run this program, I don't get this picture, which was 3 bricks high. I seem to have 4 bricks instead. Now, this might be jumping out at you why it's happening, but I kept the program simple just so that we don't have to actually find an actual bug. We can use a tool to find one that we already know about in this case. What might be the first strategy for actually finding a bug like this? Rather than just staring at your code, asking a question, trying to sort of just think through the problem, well, let's actually try to diagnose the problem more proactively. And the simplest way to do this now and years from now is honestly going to be to use a function like printf. Printf is a wonderfully useful function, not for printing formatted strings and all that, but just looking inside the values of variables that you might be curious about to see what's going on. So you know what? Let me do this. I see that there's 4 coming out, but I intended 3. So clearly something's wrong with my I variables. So let me just be a little more pedantic. Let me go inside of this loop and just temporarily say something explicit like I is %i \n, and then just plug in the value of I. Right? This is not the program I want to write. It's the program I'm temporarily writing, because now I'm going to go ahead and say make buggy /buggy. And if I look now at the output, I have some helpful diagnostic information. I is 0, and I get a hash. I is 1, and I get a hash 2, and I get a hash 3, and I get a hash. OK, wait a minute. I'm clearly going too many steps because maybe I forgot that computers are essentially counting from 0, and now, oh, it's less than or equal to. Now you see it. Right? Again, trivial example, but just by using printf, you can see inside of the computer's memory by just printing stuff out like this. And now once you figured it out, oh, so this should probably be less than 3, or I should start counting from 1. There's any number of ways I could fix this, but the most conventional is probably just to say less than 3. Now I can go ahead and delete my temporary print statement, rerun make buggy /buggy, and voila, problem solved. All right, and to this day, I do this, like whether it's making a command line application or a web application or a mobile application, it's very common to use printf or some equivalent in any language. Just poke around and see what's inside the computer's memory. Thankfully, there's more sophisticated tools than this. Let me go ahead and reintroduce the bug here, and let me go ahead and reopen my sidebar left here, and let me go ahead now and recompile the code to make sure it's current. And I'm going to run a command called debug50, which is a command that's representative of a type of program known as a debugger. And this debugger is actually built into VS Code, and all debug50 is doing for us is just automating the process of starting VS Code's built-in debugger. So this isn't even a CS50 specific tool. We've just given you a debug50 command to make it easier to start it up from the get-go. And the way you run this debugger is you say debug50 space, and then the name of the program that you want to debug. So in this case, /buggy. So you don't mention your C file, you mention your already compiled code. And what this debugger is going to let me do is most powerfully walk through my code step by step, because every program we've written thus far just kind of runs from start to finish, even if I'm not done sort of thinking through each step at a time. With the debugger, I can actually like click on a line number and say pause execution here, and the debugger will let me walk through my code 1 step at a time, 1 second at a time, 1 minute at a time at my own human pace, which is super compelling when the programs get more complicated and they might otherwise just fly by on the screen. So I'm going to click to the left of line 5 and notice that these little red dots appear, and if I click on one, it stays and gets even redder. And I'm going to now run debug50 on /buggy, and in just a moment, you'll see that a new panel opens on the left-hand side. It's doing some configuration duration of the screen. And now let me go ahead and zoom out just a little bit here so we can see more on the screen at once. And sometimes you'll see in VS Code that debug console opens up, which looks very cryptic. Just go back to terminal window if that happens, because at the terminal window is where you can still interact with your code. And let's now take a look at what's going on. If I zoom in on my buggy.c code here, you'll notice that we have the same program as before, but highlighted in yellow is line 5. Not a coincidence. That's the line I set a so-called breakpoint at. The little sort of red dot means break here, pause execution here, and the yellow line has not yet been executed. But if I now, at the top of my screen, notice these little arrows. There's one for play, there's one for this, which if I hover over it, says step over. There's another that's going to say step into. There's a third that says step out. I'm just going to use the first of these, step over, and I'm going to do this. And you'll see that the yellow highlight moved from line 5 to line 7 because now it's ready, but hasn't yet printed out that hash. But the most powerful thing here, notice, is at top left here. It's a little cryptic because there's a bunch of things going on that'll make more sense over time, but at the top there's a section called variables. Below that, something called locals, which means local to my current function main. And notice, there's my variable called I, and its current value is 0. So now, once I click step over again, watch what happens. We go from line 7 back to line 5, but look in the terminal window, one of the hashes says printed. But now it's kind of printed at my own pace. I can sort of think through this step by step. Notice that I has not changed yet. It's still 0 because the yellow highlighted line hasn't yet executed, but the moment I click step over, it's going to execute line 5. Now notice at top left, I has become 1. And nothing has printed yet because now highlighted is line 7. And so if I click step over again, we'll see the hash. And if I repeat this process at my own human comfortable pace, I can see my variables changing. I can see output changing on the screen. And I can just think about, should that have just happened? And I can pause and give thought to what's actually going on without trying to race the computer and figure it all out at once. I'm going to go ahead and just stop here because we already know what this particular problem is. And that just brings me back to my default terminal window. But this debugger, let me disable the breakpoint now so it doesn't keep breaking. This debugger will be your friend moving forward in order to step through your code, step by step at your own pace to figure out where something has gone wrong. Printf is great, but it gets annoying if you have to constantly add print this, recompile, rerun it. Oh, wait a minute, print this. Like the debugger just lets you do the equivalent, but automatically. Questions on then this debugger, which you'll see all the more hands-on over time. Questions on debugger? Yeah? Really good question. We'll see this before long, but those other buttons that I glossed over, like step into and step out of, actually let you step into specific functions if I had any more than main. So if main called a function called something, and something called a function called something else, instead of just stepping over the entire execution of that function, I could step into it and walk through its lines of code one by one. So anytime you have a problem that you're working on that has multiple functions, you can set a breakpoint in main if you want, or you can set it inside of one of your additional functions to focus your attention only on that. And we'll see examples of that over time. All right, so what else? And what's the the sort of elephant in the room, so to speak, is actually a duck in this case. Why is there this duck and all these ducks here? Well, it turns out a third genuinely recommended debugging technique is talking through problems, talking through code with someone else. Now, in the absence of having a family member or a friend or a roommate who actually wants to hear you talk about code of all things, generally programmers turn to a rubber duck or other inanimate objects if something animate is not available. And the idea behind rubber duck debugging, so to speak, is that simply by looking at your code and talking it through, OK, on line 3, I'm starting a for loop and I'm initializing I to 0. OK, then I'm printing out a hash. Just by talking through your code step by step invariably finds you having a proverbial light bulb go off over your head because you realize, wait a minute, I just said something stupid or I just said something wrong. And this is really just a proxy for any other human, teaching fellow teacher, friend, colleague. But in the absence of any of those people in the room, you're welcome to take on your way out today one of these little rubber ducks and consider using it for real anytime you just want to talk through one of your problems in CS50 or maybe life more generally. But having it there on your desk is just a way to help you hear illogic in what you think might otherwise be logical code. So printf, debugging, rubber duck debugging are just 3 of the ways you'll see over time to sort of get to the source of code that you will write that has mistakes, which is going to happen, but it'll empower you all the more to solve those mistakes. Are any questions on debugging in general or these 3 techniques? Yeah? What's the difference between step over and step into? At the moment, the only one that's applicable to the code I just wrote is step over because it means step over each line of code. If, though, I had other functions that I had written in this program, maybe lower down in the file, I could step into those function calls and walk through them one at a time. So we'll come back to this with an actual example, but step into will allow me to do exactly that. In fact, this is a perfect segue to doing a little something like this. Let me go ahead and open up maybe another file here. Actually, we'll use the same, buggy, and we're just going to write one other thing that's buggy as well. Let me go ahead up here and include as before CS50.h. Let me include standard.io.h. Let me do int main void. So all of this I think is correct so far. And let's do this. Let's give myself an int called I, and let's ask the user for a negative integer. This is not a function that exists technically yet, but I'm going to assume for the sake of discussion that it does. And then I'm just going to go ahead and print out with %i and a new line whatever the human typed in. So at this point in the story, my program I think is correct, except for the fact that get negative int is not a function in the CS50 library or anywhere else. I'm going to need to invent it myself. So suppose in this case that I declare a function called get negative int. Its return type, so to speak, should be int, because as its name suggests, I want to hand the user back an integer. And it's going to take no input to keep it simple. So I'm just going to say void there. No inputs, no special prompts, nothing like that. Let me now give myself some curly braces, and let me do something familiar perhaps now from problem set 1. Let me give myself a variable like n, and let me do the following within this block of code. Assign n the value of getInt, asking the user for a negative integer using getInt's own prompt. And I want to do this while n is less than 0, because I want to get a negative int from the user. And recall, from having used this block in the past, I can now return n as the very last step to hand back whatever the user has typed in, so long as they cooperated and gave me an actual negative integer. Now, I've deliberately made a mistake here, and it's a subtle, sort of silly mathematical one, but let me compile this program after copying now the prototype up to the top, just so I don't make that mistake again. Let me do make buggy, enter, and now let me do /buggy. I'll give it a negative integer like negative 50. That did not take. How about negative 5? Maybe it's 2. No. How about 0? All right, so it's clearly sort of working backwards or incorrectly here logically. So how could I go about debugging this? Well, I could do what I've done before. I could use my printf technique and say something explicit like n is %i, new line, comma i, comma n, just to print it out. Let me recompile buggy. Let me rerun buggy. Let me type in negative 50. OK, n is negative 50. So that didn't really help me at this point, because that's the same as before. So let me do this. Debug 50 /buggy. Oh, but I've made a mistake. So I didn't set my breakpoint yet. So let me go ahead and do this. And I'll set a breakpoint this time. I could set it here on line 8. Let's do it in main as before. Let me rerun debug 50 now on /buggy. That fancy user interface is going to pop up. It's going to highlight the line that I set the breakpoint on. Notice that on the left-hand side of the screen, I is defaulting at the moment to 0 because I haven't typed anything in yet. But let me go ahead now and step over this line that's highlighted in yellow, and you'll see that I'm being prompted. So let's type in my negative 50, enter. All right, and notice now that I'm stuck in that function So, all right. So clearly the issue seems to be in my get negative int function. So, okay, let me go ahead and stop this execution. My problem doesn't seem to be in main per se. Maybe it's down here. So that's fine. Let me set my same breakpoint at line 8. Let me rerun debug 50 one more time. But this time, instead of just stepping over that line, let's step into it. So notice line 8 is again highlighted in yellow. In the past, I've been clicking step over. Let's click step into now. And when I click step into, boom, now the debugger jumps into that specific function. And now I can step through these lines of code again and again. I can see what the value of n is as I'm typing it in. I can think through my logic. And voila, hopefully once I've solved the issue, I can exit the debugger, fix my code, and move on. So step over just goes over the line but executes it. Step into lets you go into other functions you've written. So, all right, so let's go ahead and do this. We've got a bunch of possible approaches that we can take to solving some problem. Let's go ahead and pace ourselves today. Let's take a 5-minute break here, and when we come back, we'll actually take a look at that computer's memory we've been talking about. See you in 5. All right. So let's dive back in. And up until now, both by way of week 1 and problem set 1, for the most part, we've just translated from scratch into C all of these basic building blocks like loops and conditionals, Boolean expressions, variables, so sort of more of the same. But there are features in C that we've already stumbled across already, like data types, the types of variables that doesn't exist in Scratch, but that in fact does exist in other languages. In fact, a few that we'll see before long. So to summarize the types we saw last week, just recall this little list here. We had ints and floats and longs and doubles and chars. There's also bools and also string, which we've seen a few times. But today, let's actually start to formalize what these things are and actually like what your Mac and PC are doing when you manipulate bits as an int versus a char versus a string versus something else. And see if we can put more tools into your toolkit, so to speak, so we can start quickly writing more featureful, more sophisticated programs in C. So it turns out that on most systems nowadays, though this can vary by actual computer, this is how large each of the data types typically is in C. When you store a Boolean value, a 0 or 1, a true or a false or a true, it actually uses 1 byte. That's actually a little excessive because strictly speaking, you only need 1 bit, which is 1/8 of this size. But for simplicity, computers use a whole byte to represent a bool, true or false. A char, we saw last week, is actually only 1 byte or 8 bits. And this is why ASCII, which uses 1 byte, or technically only 7 bits early on, was confined to only 256 maximally possible characters. Notice that an int is 4 bytes or 32 bits. A float is also 4 bytes or 32 bits. But the things that we call long, literally twice as long, 8 bytes or 64 bits. And so is a double. A double is 64 bits of precision for floating point values. And a string for today, we're going to leave as a question mark, because we'll come back to that later today and next week as to how much space a string takes up. But suffice it to say, it's going to take up a variable amount of space, depending on whether the string is short or long, but we'll see exactly what that means before long. So here's a photograph of a typical piece of memory inside of your Mac or PC or phone, and odds are it might be just a little smaller in some devices. This is known as RAM, or random access memory. And each of these little black chips on this circuit board, the green thing, these little black chips are where zeros and ones are actually stored. Each of those stores some number of bytes, maybe megabytes, maybe even gigabytes nowadays. So let's actually focus on just one of those chips just to give us a sort of zoomed in version thereof. And let's consider the fact that even though we don't have to care exactly how this kind of thing is made, if this is like 1 gigabyte of memory for the sake of discussion, it stands to reason that if this thing is storing 1 billion bytes, 1 gigabyte, then we can number them kind of arbitrarily. Like maybe this will be byte 0, 1, 2, 3, 4, 5, 6, 7, 8, and then maybe way down here in the bottom right corner is byte number 1 billion. Right? We can just number these things as might be our convention. So let's actually draw that graphically, not with a billion squares, but fewer than those. And let's just zoom in further and consider that, all right, at this point in the story, let's abstract away all the hardware and all the little wires and just think of memory as taking up, or rather, just think of data as taking up some number of bytes. So for instance, if you were to store a char in a computer's memory, which was 1 byte, it might be stored literally at this like top left-hand location of this black chip of memory. If you were to store something like an integer that uses 4 bytes, well, it might use 4 of those bytes, but they're going to be contiguous, back to back to back in this case. If you were to store a long or a double, you might actually need 8 bytes. So I'm just kind of filling in these squares to represent how much memory a given variable of some data type would take up, 1 or 4 or 8 in this case here. Well, from here, let's go ahead and just abstract away from all of the hardware and just really focus on memory as being a grid, or really like a canvas that we can paint any types of data onto that we want. At the end of the day, all of this data is just going to be zeros and ones, but it's up to you and I to sort of build abstractions on top of that, things like actual numbers and colors and images and movies and beyond. But we'll start lower level here first. Suppose I had a program that needs 3 integers, like a simple program whose purpose in life is to like average your 3 scores on an exam or some such thing. And suppose that your 3 scores were these, 72 and 73, not too bad, and 33, which is particularly low. Let's go ahead and write a program that actually does this kind of averaging for us. Let me go back to VS Code here. Let me open up a file called scores.c. And let me go ahead and implement this as follows. Let me include standard io.h at the top, int main void as before, and then inside of main, let me go ahead and declare score1, which is 72, give me another score, 73, and then a third score called score3, which is going to be 33. And now I'm just going to use printf to print out the average of those things. And I can do this in a few different ways, but I'm going to just print out %f, and I'm going to do score1 plus score2 plus score3 divided by 3, close parenthesis, semicolon. So just some relatively simple arithmetic, just to compute the average of 3 scores if I'm curious like what my average grade is in the class with these 3 assessments. All right, let me go ahead now and do make scores. All right, so I've somehow made an error already, but this one is actually germane to a problem we hopefully won't encounter too frequently. What's going on here? So underline is score1 plus score2 plus score3 divided by 3. Format specifies type double, but the argument has type int. Well, what's going on here? Because the arithmetic seems to check out. Yeah. Correct. And we'll come back to this in more detail. But indeed, what's happening here is I'm adding 3 ints together, obviously, because I defined them right up here. And I'm dividing by another int, 3. But the catch is, recall that C, when it performs math, treats all of these things as integers. But integers are not floating point values. So if you actually want to get a precise average for your score without throwing away the remainder, everything after the decimal point, it turns out in this case we're going to have to convert this whole expression somehow to a float. And there's a few ways to do this. But the easiest way for now, I'm just going to go ahead and do this up here. I'm going to change the divide by 3 to divide by 3.0, because it turns out, long story short, in C, so long as one of the values participating in an arithmetic expression like this is something like a float, the rest will be treated as, promoted to, so to speak, a floating point value as well. So let me now recompile this code with make scores, enter. This time it worked OK, because I'm treating a float as a float. And let me do /scores, enter. All right, my average is 59.33333, and so forth. All right, so the math presumably checks out, floating point imprecision per last week aside. But let's consider the design of this program. Like, what is kind of bad about it? Or if we maintain this program longer term, are we going to regret the design of this program? What might not be ideal here? Yeah. Yeah, so in this case, I have hard-coded my 3 scores. So if I'm hearing you correctly, this program is only ever going to tell me this specific average. I'm not even using something like get int or get float to get 3 different scores. So that's not good. And suppose that we wait later in the semester, I think other problems could arise. Yeah. I can't reuse the number because I haven't stored the average in some variable, which in this program, not a big deal, but certainly if I wanted to reuse it elsewhere, that's a problem. And let's fast forward again a little later in the semester. I don't just have 3 test scores or exam scores. Maybe I have 4 or 5 or 6. Where might this take us? Yeah, I've sort of capped this program at 3, and honestly, this is just kind of bordering on copy-paste. Even though the variables, yes, have different names, score 1, score 2, score 3, imagine doing this for like a whole gradebook for a class, having score 4, 5, 6, 11, 10, 12, 20, 30. Like, that's a lot of variables. And you can imagine just how ugly the code starts to get if you're just defining variable after variable after variable. So it turns out there are better ways in languages like C if you actually want to have multiple values stored in memory that happen to be of the same data type. And so let's take a look back at this memory here to see what these things might look like in memory. Here's that grid of memory, and each of these recall represents a byte. So just to be clear, if I store score 1 in memory first, how many bytes will it take up? So 4, aka 32 bits. So I might draw score 1 as filling up this part of the memory. It's really up to the computer as to whether it goes here or down there or wherever. I'm just keeping the pictures clean though for today, from the top left on down. If I then declare another variable called score 2, it might end up over there, also taking up 4 bytes, and then score 3 might end up here. And so that's just representing what's going on inside of the computer's memory. But technically speaking, to be clear, per week 0, what's really being stored in the computer's memory are patterns of zeros and ones. 32 total in this case, because 32 bits is 4 bytes. But again, it sort of gets boring quickly to think in and look at binary all the time. So we'll generally abstract this away as just using decimal numbers in this case instead. But there might be a better way to store not just 3 of these things, but maybe 4, maybe 5, maybe 10, maybe more, by declaring one variable to store all of them instead of 3 or 4 or 5 or more individual variables. And the way to do this is by way of something generally known as an array. An array is another type of data that allows you to store multiple values of the same type back to back to back. That is to say, contiguously. So an array can let you create memory for 1 int, or 2, or 3, or even more than that, but describe them all using the same variable name, the same one name. So for instance, if for one program I only need 3 integers, but I don't want to sort of messily declare them as score 1, score 2, score 3, I can actually do this instead. And this is today's first new piece of syntax, the square brackets that we're now seeing. This line of code here is similar to int score 1 semicolon, or int score 1 equals 72 semicolon. This line of code is declaring for me, so to speak, an array of size 3. And that array is going to store 3 integers. Why? Because the type of that array is an int here. The square brackets tell the computer how many ints you want, in this case 3, and the name is of course scores, which in English I've just deliberately pluralized now so that I can describe this array as storing multiple scores indeed. So if I want to now assign values to this variable called scores, I can do code like this. I can say scores bracket 0 equals 72, scores bracket 1 equals 73, and scores bracket 2 equals 33. The only thing weird there is admittedly the square brackets, which are still new, but we're also notice 0 indexing things. To 0 index means to start counting at 0. We've talked about that before. Our for loops have generally been 0 indexed. Arrays in C are 0 indexed, and you do not have choice over that. You can't just start counting at 1 in arrays just because you prefer to. You'd be sacrificing one of the elements. You have to start in arrays counting from 0. So out of context, this doesn't necessarily solve the problem, but it definitely is going to once we have more than even 3 scores here. In fact, let me go ahead and change this program a little bit. Let me go back to VS Code here, and let me go ahead and delete these 3 lines here, and let me replace it with a scores variable that's ready to store 3 total integers. And then let me go ahead and initialize them as follows. Scores bracket 0 is 72 as before. Scores bracket 1 is going to be 73. Scores bracket 2 is going to be 33. Notice I do not need to say int before any of these lines because that's been taken care of already for me on line 5, where I already specified that everything in this array is going to be an int. Now down here, this code needs to change because I no longer have 3 variables, score 1, 2, and 3. I have 1 variable, but that I can index into. I'm going to here then do scores bracket 0 plus scores bracket 1 plus scores bracket 2, which is equivalent to what I did earlier, giving back those 3 integers, but notice I'm using the same variable name every time. And again, I'm using this new square bracket notation to quote-unquote index into the array to get at the first int, the second int, and the third, and then to do it again down here. Now this program's still not really solving all the problems we described. Like I still can only store 3 scores, but we'll come back to something like that before long. But for now, we're just introducing a new syntax and a new feature whereby I can now store multiple values in the same variable. Well, let's enhance this a bit more. Instead of hard coding these scores, as was identified as a problem, let's go ahead and use getInt to ask the user for a score. Let's then use getInt to ask the user for another score. Let's use getInt to ask the user for a third score, storing them in those respective locations. And now, if I go ahead and save this program, recompile scores, I've messed up here, but now these errors should be getting a little familiar. What mistake did I make? Let me give folks a moment. CS50.h. So that was not intentional, so still making mistakes all these years later. I need to include CS50.h. Now I'm going to go back to the bottom in the terminal window, make scores. OK, we're back in business./scores. Now the program's getting a little more interesting. So maybe this year was better, and I got 100 and a 99 and a 98, and there my average is 99.0000. So now it's a little more dynamic. So it's a little more interesting, but it's still capping the number of scores at 3, admittedly. But now I've kind of introduced another sort of symptom of bad programming. There's this expression in programming too called code smell, where like something smells a little off, and there's something off here in that I could do better with this code here. Does anyone see an opportunity to improve the design of this code here if my goal still is just to get 3 scores from the user, but without it like smelling kind of bad? Yeah. Yeah, exactly. Those lines of code are almost identical, and honestly, the only thing that's changing is the number, and it's just incrementing by 1. We have all of the building blocks to do this better, so let me go ahead and improve this. Let me go ahead and delete that code. Let me go ahead now and have a for loop. So for int I gets 0, I less than 3, I plus plus. Then inside of this for loop, I can distill all 3 of those lines into something more generic, like scores bracket I equals getInt, and now ask the user just once via getInt for score. So this is where arrays start to get pretty powerful. You don't have to hard code. That is literally type in all these magic numbers like 0, 1, and 2. You can start to do it programmatically as you propose with a loop. So now I've kind of tightened things up. I'm now dynamically getting 3 different scores, but putting them in 3 different locations. And so this program ultimately is going to work pretty much the same. Make scores, /scores, and 100, 99, 98, and we're back to the same answer. But it's a little better designed too. If I really want to nitpick, there's something that still smells a little bit here. The fact that I have indeed this magic number 3 here that really kind of has to be the same as this number here. Otherwise, who knows what's going to go wrong? So what might be a solution per last week to kind of cleaning that code up further too? OK, so we could leave it up to the user's discretion. And so we could actually do something like this. Let me take this a few steps ahead. Let me say something like int n gets getInt, how many scores, question mark. Then I could actually change this to an n, and then this to an n, and indeed make the whole program dynamic. Ask the human how many tests have there been this semester. Then you can type in each of those scores, because the loop is going to iterate that many times, and then you'll get the average of 1 test, 2 tests, 3, I lost another, or however many scores that were actually specified by the user. Yeah, question? How many bytes are used in an array? So the purpose of an array is not to save space. It's to eliminate having multiple variable names, because that just gets very messy quickly if you literally have score 1, score 2, score 3, score 99. That's literally like 99 different variables potentially that you could actually collapse into one variable that has 99 locations, if you will, at different indices or indexes, as someone would say. The index for an array is whatever's in the square brackets. So it's a good question. So I'm using ints for everything, and honestly, we don't really need ints for scores because I'm not really likely to get a 2 billion on a test anytime soon. And so you can actually use different data types. And that list we had on the screen earlier is not all of them. There's actually a data type called short, which is literally shorter than an int. You could actually technically use char in some form, or even other data types as well. Generally speaking, in the year 2021, these tend to be overly optimized decisions. Like everyone just uses ints, even though no one's going to get a test score that's 2 billion or more, because int is just kind of the go-to. Years ago, memory was expensive, and every one of your instincts would have been spot on because memory is so tight. But nowadays, we don't worry as much about it. Yeah. So what is the difference between dividing two ints and not getting an error, as you might have encountered in a program like Cache, versus dividing two ints and getting an error like I did a moment ago? The problem with the scenario I created a moment ago was printf was involved. And I was telling printf to use %f, but I was giving printf the result of dividing integers by another integer, so it was printf that was yelling at me. And I'm guessing in the scenario you're describing for something like Cache, printf was not involved in that particular line of code. So that's the difference there. All right, so we now have this ability to create an array, and an array can store multiple values. What then might we do that's more interesting than just storing numbers in memory? Well, let's take this one step further. As opposed to just storing 72, 73, 33, or 100, 99, 98 at these given locations, because again, an array gives you one variable name, but multiple locations or indices therein, bracket 0, bracket 1, bracket 2, on up, if it were even bigger than that. Let's now start to consider something more modest, like simple chars. Chars being 1 byte each, so they're even smaller, they take up much less space. And indeed, if I wanted to say a message like hi, I could use 3 variables. If I wanted a program to print hi, hi exclamation point, literally, I could of course store those in 3 variables, like C1, C2, C3. And let's just, for the sake of discussion, let's go ahead and whip this up real quickly. Let me create a new program here now in VS Code. This time I'm going to call it hi.c. And I'm not going to bother with the CS50 library here. I just need the standard IO one for now. Int main void. And then inside of main, I'm going to simply create 3 variables. And this is already hopefully striking you as a bad idea, but we'll go down this road temporarily with C1 and C2 and finally C3, storing each character in the phrase I want to print. And I'm going to go ahead now and print this in a different way than usual. Now I'm dealing with chars, and we've generally dealt with strings, which was easier certainly last week. But %c will let me print out 3 chars, and like C1, C2, and C3. So kind of a stupid way of printing out a string. So we already have a solution to this problem last week, but let's just poke around at what's actually going on underneath the hood here. So let's make hi, /hi, and voila. No surprise, but we again could have done this last week with a string and just one variable, or even 0 at that. But let's go ahead now and start converting these characters to their apparent numeric equivalents like we talked about in week 02. Let me go ahead and modify these %c's just to be fun to be %i's, and let me just add some spaces so that there are gaps between each of them. Let me now recompile hi, and let me rerun it. And just to guess, what should I see on the screen now? Any guesses? Yeah. The ASCII values. And it's intentional that I keep using the same word, hi, because it should be, hopefully, the old friends 72, 73, and 33, which is to say that C knows about ASCII or equivalently Unicode and can do this conversion for us automatically, and it seems to be doing it implicitly for us, so to speak. Notice that C1, C2, and C3 are obviously chars, but printf is able to tolerate printing them as integers. If I really wanted to be pedantic, I could use this technique, again known as typecasting, where I can actually convert one data type to another if it makes logical sense to do so. And at the end of the day, we saw in week 0, chars or characters are just numbers, like 72, 73, and 33. So I can actually use this parenthetical expression to convert, incorrectly, 3 chars to 3 integers instead. So that's what I meant to type the first time. There we go, strike 2 today. So parenthesis, int, close parenthesis, just says take whatever variable comes after this, C1 or C2 or C3, and convert it to an int. The effect is going to be no different here. Make hi, and then rerunning, then running /hi still works the same, but now I'm explicitly converting chars to ints. And we can do this all day long, chars to ints, floats to ints, ints to floats. Sometimes it's equivalent. Other times you're going to lose information. Taking a float to an int just intuitively is going to throw away everything after the decimal point, because after all, an int has no decimal point. But for now, I'm going to go ahead and rewind to the version of this that just did implicit type conversion or implicit casting, just to demonstrate that we can indeed see the values underneath the hood. All right, let me go ahead and do this now the week 1 way. This was kind of stupid. Let's just do printf, quote unquote. Actually, let's do this. String s equals quote unquote hi, and then let's go ahead and do a simple printf with %s, printing out s is there. So now I've rewound to last week where we began this story, but you'll notice that if we keep playing around with this, whoops, what did I do? Oh, let me introduce the CS50 library here. More on that before long. Let me go ahead and recompile, rerun this. We seem to be coding in circles here. Like I've just done the same thing multiple different ways. But there's clearly an equivalence then between sequences of chars and strings. And if you do it the real pedantic way, you have like 3 different variables, C1, C2, C3, representing hi exclamation point, or you can just treat them all together like this, hi exclamation point. But it turns out that strings are actually implemented by the computer in a pretty now familiar way. What might a string actually be as of this point in the story? Where are we going with this? Let me try to look farther back. Yeah, way back? Yeah. Yeah, a string might be, and indeed is, just an array of characters. So last week we just took for granted that strings exist. Technically, strings exist, but they're implemented as arrays of characters, which actually opens up some interesting possibilities for us. Because let me see if I can do this. Let me try to print out now 3 integers again. But if string s is but an array, as you propose, maybe I can do s bracket 0, s bracket 1, and s bracket 2. So maybe I can start poking around inside of strings, even though we didn't do this last week, so I can get at those individual values. So make hi, /hi, and voila, there we go again. It's the same 72, 73, 33, but now I'm sort of hopefully wrapping my mind around the fact that, all right, a string is just an array of characters, and arrays, you can index into them using this new square bracket notation. So I can get at any one of these individual characters and heck, convert it to an integer, like we did in week 0. As I might. But let me get a little curious now, too. What else might be in the computer's memory? Well, let's toggle back to the depiction of these same things. Here might be how we originally implemented hi with 3 variables, C1, C2, C3. Of course, that maps to these decimal digits or equivalent these binary values. But what was this looking like in memory? Literally, when you create a string in memory like this, string s equals quote unquote hi, let's consider what's going on underneath the hood, so to speak. Well, as an abstraction, a string, it's hi exclamation point taking up, it would seem, 3 bytes. Right? I've gotten rid of the bars there because if you think of a string as a type, I'm just going to use one big box of size 3. But technically, a string we've just revealed is an array, and the array is of size 3. So technically, if the string's called s bracket 0 will give you the first character, s bracket 1 the second, and s bracket 3 the third. But let me ask this question now. If this, at the end of the day, is the only thing in your computer, memory, and the ability, like a canvas, to draw zeros and ones or numbers or characters or whatever on it, but that's it. Like this is what your Mac and PC and phone ultimately reduce to. Suppose that I'm running a piece of software, like a text messenger, and now I write down by exclamation point. Well, where might that go in memory? Well, it might go here, BYE. And then the next thing I type might go here, 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 and so forth. My memory just might get filled up over time with things that you or someone else are typing. But then how does the computer know if potentially BYE exclamation point is right after HI exclamation point, where one string ends and the next one begins? Right? All we have are bytes or zeros and ones. So if you were designing this, how would you implement some kind of delimiter between the two or figure out what the length of a string is? What do you think? Okay, so the right answer is use a null character, and for those who don't know, what does that mean? Yeah, so it's a special character. Let me describe it as a sentinel character. Humans decided some time ago that, you know what, if we want to delineate where one string ends and where the next one begins, we just need some special symbol. And the symbol they'll use is generally written as \0. This is just shorthand notation for literally 80 bits. 00000000, and the nickname for 80 bits in this context is null, N-U-L, so to speak. And we can actually see this as follows. If you look at the corresponding decimal digits, like you would do by just doing out the math or doing the conversion like we've done in code, you would see for storing high, 72, 73, 33, but then one extra byte that's sort of invisibly there, but that is all zeros. And now I've just written it as the decimal number 0. The implication of this is that the computer is apparently using not 3 bytes to store a word like high, but 4 bytes. Whatever the length of the string is plus 1 for this special sentinel value that demarcates the end of the string. So we might draw it like this instead, and this character is again sort of pronounced null, or written N-U-L. So that's all, right? If humans at the end of the day just have this canvas of memory, they just needed to decide, all right, well, how do we distinguish one string from another? Because it's a lot easier with chars individually. It's a lot easier with ints. It's even easier with floats. Why? Because per that chart earlier, every character is always 1 byte. Every int is always 4 bytes. Every long is always 8 bytes. How long is a string? Well, high is 1, 2, 3 with an exclamation point. Bi is 1, 2, 3, 4 with an exclamation point. David is D-A-V-I, D5 without an exclamation point. And so a string can be any number of bytes long. So you somehow need to draw a line in the sand to separate in memory one string from another. So what's the implication of this? Well, let me go back to code here. Let's actually poke around. This is a bit dangerous, but I'm going to start looking at memory locations past my string here. So let me go ahead and recompile make high. Whoops, what did I do here? Oh, I forgot a format code. Let me add one more %i. Now let me go ahead and rerun make high, /hi, enter. There it is. So you can actually see in the computer, unbeknownst to you previously, that there's indeed something else going on there. And if I were to make like one other variant of this program, let's get rid of just this one word, and maybe let's have 2. So let me give myself another string called t, for instance, just as common convention, with by exclamation point. Let me then go ahead and print out with %s, s, and let me also print out with %s, whoops, printf, print out t as well. Let me just recompile this program, and obviously the out, this is what happens when I go too fast. All right, third mistake today, close quote, as I was missing, make high. Fourth mistake today, make high, /high. Okay, voila. Now we have a program that's printing both high and bi, only so that we can consider what's going on in the computer's memory. If s is storing high, and apparently one bonus byte that demarcates the end of that string, bi is apparently going to fit into the location directly after. And it's wrapping around, but that's just an artist's rendition here. But bi, bye, exclamation point, is taking up 1, 2, 3, 4, plus a 5th byte as well. Whew. All right, any questions on this underlying representation of strings? And we'll contextualize this before long so that this isn't just like, okay, who really cares? This is going to be the source of actually implementing things, in fact, for problems too, like cryptography and encryption and actually scrambling actual human messages. But some questions first. A good question, too, and let me summarize as if we were instead to use chars all the time, we would indeed have to know in advance how many chars you want for a given string that you're storing. How then does something like getString work? Because when CS50 wrote the getString function, we obviously don't know how long the words are going to be that you all are typing in. It turns out next 2 weeks from now, we'll see that getString uses a technique known as dynamic memory allocation, and it's going to grow or shrink the array automatically for you. But more on that soon. Other questions? Good question. Why are we using a null value? Isn't it wasting a byte? Yes, but I claim there's really no other way to distinguish the end of one string from the start of another unless we make some sort of notation, so to speak, in memory. All we have at the end of the day inside of a computer are bits. Therefore, all we can do is spend those bits in some creative way to solve this problem. And so we're minimally going to spend 1 byte to solve this problem here. Yeah? If you don't, how does the computer know to move to the next line when you have a \n? So \n, even though it looks like 2 characters, it's actually stored as just 1 byte in the computer's memory. There's a mapping between it and an actual number. And you can see that, for instance, on the ASCII chart from the other day. It would be. If I had put a \n in my code here, right after the exclamation point here and here, that would actually shift everything in memory because we would need to make room for a \n here and another one over here. So it would take 2 more bytes, exactly. Other questions? So if I exclamation point is written binary and ASCII to 72, 73, 33, if you were to write those numbers in the string and convert them into binary, how would the computer know what's 72 and what's 8? And what's the last thing you said? It's context sensitive. So if at the end of the day, all we're storing is these numbers, like 72, 73, 33, recall that it's up to the program to decide based on context how to interpret them. And I simplified this story in week 0, saying that Photoshop interprets them as RGB colors, and iMessage, our text messaging program, interprets them as letters, and Excel interprets them as numbers. How those programs do it is by way of variables, like string and int and float. And in fact, later this semester, we'll see a data type via which you can represent a color as a triple of numbers, and red value, a green value, and a blue value. So we'll see other data types as well. Yeah? Really interesting question. Why could we not just make all data types variable in size? And some languages, some libraries do exactly this. C is an older language, and so because memory was expensive, memory was limited, the reality was you gain benefits from just standardizing the size of these things. You also get performance increases in the sense that if you know every int is 4 bytes, you can very quickly, and we'll see this next week, jump from integer to another in memory just by adding 4 inside of those square brackets. You can very quickly poke around, whereas if you had variable length numbers, you would have to kind of follow, looking for the end of it. You have to look at more locations in memory. So that's a topic we'll come back to, but it was generally for efficiency. And other question, yeah? Good question. Why not store the okay, same one. Why not store the null character at the beginning? You could. Let's see. Why not store it at the beginning? You could do that. You could absolutely. Well, could you do this? If you were to do that at the beginning. Short answer, no. OK, I retract that. No, because I finally thought of a problem with this. If you store it at the beginning instead, we'll see in just a moment how you can actually write code to figure out where the end of a string is. And the problem there is you wouldn't necessarily know if you eventually hit a 0 at the end of the string because it's the number 0 in the context of like Excel using some memory, or if it's the context of some other data type altogether. So the fact that we've standardized strings as ending with null means that we can reliably distinguish one variable from another in memory. And that's actually a perfect segue now to actually using this primitive to building up our own code that manipulates these things at a lower level. So let me go ahead and do this. Let me create a new file this time called length, and let's just use this basic idea to figure out what the length of a string is after it's been stored in a variable here. So let's go ahead and do this. Let me include both the CS50 header and the standard I/O header, give myself int main void again here, and inside of main, let me go ahead and do this. Let me prompt the user for a string s, and I'll ask them for a string like their name here. And then let me go ahead and, actually, let me name it more verbosely name this time. And now let me go ahead and do this. Let me iterate over every character in this string in order to figure out what its length is. So initially, I'm going to go ahead and say this, int length equals 0, because I don't know what it is yet, so we're going to start at 0. And then while the following is true, while, do I want to do this? Let me change this to I, just for clarity. Let me go ahead and do this. While name bracket I does not equal that special null character. So I typed it on the slide as NUL, but you don't write NUL in code. You actually use its numeric equivalent, which is \0 in single quotes. While name bracket I does not equal the null character, I'm going to go ahead and increment I to I++. And then down here, I'm going to print out the value of I to see what we actually get. Printing out the value of I. All right, so what's going to happen here? Let me go ahead and run make length. Fortunately, no errors. /length, and let me type in something like hi exclamation point enter. And I get 3. Let me try by exclamation point enter. And I get 4. Let me try my own name, David, enter. 5, and so forth. So what's actually going on here? Well, it seems that by way of this for loop, we are specifying a local variable called I initialized to 0, because we're figuring out the length of the string as we go. I'm then asking the question, does location 0, that is I, in the name string, which we now know is an array, does it not equal \0? Because if it doesn't, that means it's an actual character like H or B or D, so let's increment I. Then let's come back around to line 9 and let's ask the question again. Now I equals 1, so does name bracket 1 not equal \0? Well, if it doesn't, and it won't if it's an I or a Y or an A based on what I typed in, we're going to increment I once more. Fast forward to the end of the story. Once I get to the end of the string, technically one space past the end of the string, name bracket I will equal \0, so I don't increment I anymore. I end up just printing the result. So what we seem to have here with some low-level C code, just this while loop, is a program that figures out the length of a given string that's been typed in. Let's practice our abstraction and decompose this into maybe a helper function here. Let me actually grab all of this code here. And let me assume for the sake of discussion for a moment that I can just call a function now called string length, and the length of the string is name that I want to get, and then I'll go ahead and print out, just as before, with %i, the length of that string. So now I'm abstracting away this notion of figuring out the length of the string. That's an opportunity for me to create my own function. If I want to create a function called string length, I'll claim that I want to take a string as input, and what should I have this function return as its return type? What should getString presumably return? Yeah. An int, right? An int makes sense. Float really wouldn't make sense because we're measuring things that are integers, in this case, the length of something. So indeed, let's have it return an int. I can pretty much use the same code as before, so I'm just going to paste what I cut earlier in the file. And the only thing I have to change here is the name of the variable, because now this function, I decided kind of arbitrarily that I'm going to call it s, just to be more generic. So I'm going to look at s bracket I at each location, and I don't want to print it at the end. This would be a side effect. What's the line of code I should include here if I actually want to hand back the total length? Yeah. Say again? Return I in this case. So I'm going to go ahead and return I, not print it, because now my main function can use the return value. Value stored in length and print it on the next line itself. I just need a prototype, so that's my one forgivable copy paste here. I'm going to rerun make length. Hopefully I didn't screw up. I didn't. /length. I'll type in hi. Oops. I'll type in hi again. That works. I'll type in by again, and so forth. All right. So now we have a function that determines the length of a string. Well, it turns out we didn't actually need this all along. It turns out that we can get rid of my own custom string length function here. I can definitely delete the whole implementation down here, because it turns out in a file called string.h, which is a new header file today, we actually have access to a function called, more succinctly, strlen, S-T-R-L-E-N, which literally does that. This is a function that comes with C, albeit in the string.h header file, and it does pretty much what we just implemented manually. So here's an example of, admittedly, a wheel we just reinvented, but no more. We don't have to do that. And how do you know what kinds of functions exist? Well, let me actually pop out of my browser here to a website that is a CS50's incarnation of what are called manual pages. It turns out that in a lot of systems, Macs and Unix and Linux systems, including the Visual Studio Code instance that we have in the cloud, there are publicly accessible manual pages for functions. They tend to be written very expertly in a way that's not very beginner-friendly. So what we have here at manual.cs50.io is CS50's version of manual pages that have this less comfortable mode that give you a sort of cheat sheet of very frequently used helpful functions in C, and we've translated the sort of expert notation to things that a beginner can understand. So for instance, let me go ahead and search for string up at the top here, you'll see that there's documentation for our own getString function. But more interestingly, down here, there's a whole bunch of string-related functions that we haven't even seen most of yet. But there's indeed one here called strling, calculate the length of a string. And so if I actually go to strling here, I'll see some less comfortable documentation for this function. And the way a manual page typically works, whether in CS50's format or any other system, is you see typically a synopsis of what header files you need to use the function. So you would copy paste these couple of lines here. You see what the prototype is of the function, so that you know what its inputs are, if any, and its outputs are, if any. Then down below you might see a description, which in this case is pretty straightforward. This function calculates the length of s. Then you see what the return value is, if any, and you might even see an example, like this one that we've whipped up here. So these manual pages, which are, again, accessible here, and we'll link to these in the problem sets moving forward, are pretty much the place to start when you want to figure out, has a wheel been invented already? Is there a function that might help me solve some problem set problems so that I don't have to really get into the weeds of doing all of those lower level steps as I've had? Sometimes the answer is going to be yes, sometimes it's going to be no. But again, the point of our having just done this together is to reveal that even the functions you start taking for granted, they all reduce to some of these basic building blocks. At the end of the day, this is all that's inside of your computer. It's zeros and ones. We're just learning now how to harness those and how to manipulate them ourselves. All right, any questions here on this? Any questions at all? Yeah. Good question. Is it so common that you would have to specify it or not? You do need to include its header files, because that's where all of those prototypes are. You don't need to worry about linking it in with -l anything. And in fact, moving forward, you do not ever need to worry about linking in libraries when compiling your code. We, the staff, have configured Make to do all of that for you automatically. We want you to understand that it is doing it, but we'll take care of all of the -ls for you. But the onus is on you for the prototypes and the header files. Other questions on these representations or techniques? Yeah. A good question. If you were to have a string with actual spaces in it, that is multiple words, what would the computer actually do? Well, for this, let me go to ASCIIchart.com, which is just a random website that's my go-to for the first 127 characters of ASCII. This is, in fact, what we had a screenshot of the other day. And if you look here, it's a little non-obvious, but SP is space. If a computer were to store space, it would actually store the decimal number 32, or technically the pattern of zeros and ones that represent the number 32. All of the US English keys that you might type in the keyboard can be represented with a number, and using Unicode, can you express even things like emojis in other languages? Yeah. Good question. Only strings are accompanied by nulls at the end, because every other data type we've talked about thus far is of well-defined finite length. 1 byte for char, 4 bytes for ints, and so forth. If we think back to last week, we did end the week with a couple of problems. Integer overflow, because like 4 bytes, heck, even 8 bytes is sometimes not enough. We also talked about floating point imprecision. Thankfully, in the world of scientific computing and financial computing, there are libraries you can use that draw inspiration from this idea of a string, and they might use 9 bytes for an integer value, or maybe 20 bytes. You can count really high, but they will then start to manage that memory for you. And what they're really probably doing is just grabbing a whole bunch of bytes and somehow remembering how long the sequence of bytes is. That's how these higher level libraries work too. All right, this has been a lot. Let's take one more break here. We'll do like a 7-minute break here, and when we come back, we'll flesh out a few more details. All right. So we just saw strling as an example of a function that comes in the string library. Let's start to take more of these library functions out for a spin, so we're not relying only on the built-ins that we saw last week. Let me go ahead and switch over to VS Code, and let me create a file called, say, string.h, just to kind of apply this lesson learned as follows. Let me go ahead and include CS50.h. Let me include standard.io.h, and this new thing, string.h as well at the top. I'm going to do the usual int main void here. And then in this program, suppose for the sake of discussion that I didn't know about %s for printf, or heck, maybe early on there was no %s format code. And so there was no easy way to print strings. Well, at least if we know that strings are just arrays of characters, we could use %c as a workaround, so to speak, a solution to that sort of contrived problem. So let me ask myself for a string s by using getString here, and I'll ask the user for some input. And then let me go ahead and print out, say, output. And all I want to do is print back out what the user typed. Now, the simplest way to do this, of course, is going to be like last week, printf %s, and plug in the s, and we're done. But again, for the sake of discussion, I forgot about, or someone didn't implement %s. So how else could we do this? Well, in pseudocode or in English, like what's the gist of how we could solve this problem? Printing out the string s on the screen without using %s. How might we go about solving this? Just in English, high level. What would your pseudocode look like? Yeah? OK, so just print each letter, and maybe more precisely, like some kind of loop. Like let's iterate over all of the characters in s and print one at a time. So how can I do that? Well, for int I gets 0 is kind of the go-to starting point for most loops. I is less than, OK, how long do I want to iterate? Well, it's going to depend on what I type in, but that's why we have Sterling now. So iterate up to the length of s, and then increment I with ++ on each iteration. And then let's just print out %c with no new line, because I want everything on the same line, whatever the character is at s bracket I. And then at the very end, I'll give myself that new line just to move the cursor down to the next line so the $sign's not in a weird place. All right, so let's see. If I didn't screw up any of the code, make string, enter. So far, so good. String, and let me type in something like hi, enter. And I see output of hi, too. Let me do it once more with by, enter, and that works, too. Notice I very deliberately and quickly gave myself 2 spaces here and 1 space here just because I literally wanted these things to line up properly, and input is shorter than output. But that was just a deliberate formatting detail. So this code is correct, which is a claim I've made before, but it's not well designed now. It is well designed in that I'm using someone else's library function. Like I've not reinvented a wheel. There's no line 15 or below. I didn't implement string length myself. So I'm at least kind of practicing what I've preached. But there's still an imperfection, a suboptimality. This one's really subtle, though. And you have to think about how loops work. What am I doing that's not super efficient? Yeah, in back? Yeah, this is a little subtle, but if you think back to the basic definition of a for loop, and recall when I highlighted things last week, what happens? Well, the first thing is that I gets set to 0. Then we check the condition. How do we check the condition? We call Sterling on s. We get back an answer like 3 if it's hi exclamation point. And 0 is less than 3, so that's fine. And then we print out the character. Then we increment I from 0 to 1. We recheck the condition. How do I recheck the condition? I call Sterling of s, get back the same answer, 3. Compare 3 against 1. We're still good, so we print out another character. I gets incremented again. I is now 2. We check the condition. What's the condition? Well, what's the string length of s? It's still 3. 2 is still less than 3. So I keep asking the same question sort of stupidly because the string is presumably never changing in length. And indeed, every time I check that condition, that function is going to get called. And every time the answer for hi is going to be 3, 3, 3. So it's a marginal sort of suboptimality, but I could do better, right? Like don't ask multiple times questions that you can remember the answer to. So how could I remember the answer to this question and ask it just once? How could I remember the answer to this question? Let me say, yeah, back there. So stored in a variable, right? That's been our answer most any time we want to keep something around. So how could I do this? Well, I could do something like this. Int maybe length equals Sterling of s. Then I can just change this function call, so to speak. And let me fix my spelling here. Let me fix this to be now comparing against length. And this is now OK, because now Sterling is only called once on line 9. And I'm reusing the value of that variable, aka length again and again and again, so that's more efficient. Turns out that for loops actually let you declare multiple variables at once, so we can actually do this a little more elegantly, all in one line. And this is just now some syntactic improvement. I could actually do something like this. N equals Sterling of s And then I could just say n here. Or I could call it length, but heck, while I'm being succinct, I'm just going to use n for number. So now it's just a marginal change, but I've now declared two variables inside of my loop, I and n. I is set to 0, n is set to the string length of s. But now, hereafter, all of my condition checks are just I less than n, and n is never now changing. All right, so a marginal improvement there. Now that I've used this new function, let's use some other functions that might be of interest. Let me go ahead and write a quick program here that maybe like capitalizes the beginning of, that changes to uppercase some string that the user types in. So let me go ahead and code a file called uppercase.c. Up here, I'll use my new friends, CS50.h and standard.io and string.h. So standard.io and string.h. So just as before, int main void. And then inside of main, what I'm going to do this time is let's ask the user for a string s using getString, asking them for the before value. And then let me go ahead and just print out something like after, so that just so I can see what the uppercase version thereof is. And then after this, let me go ahead and do the following. For int I equals 0, let's practice that same lesson. So n equals the string length of s. I is less than n, I plus plus. So really nothing new, really, fundamentally yet. How do I now convert characters from lowercase, if they are, to uppercase? In other words, if I type in hi, hi in lowercase, I want my program now to uppercase everything to capital H, capital I. Well, how can I go about doing this? Well, you might recall that there is this ASCII chart. So let's just consult this real quick. On ASCIIchart.com, we've looked at this last week. Notice that capital A is 65, capital B is 66, capital C is 67, and heck, here's lowercase a, lowercase b, lowercase c, and that's 97, 98, 99. And if I actually do some math, there's like a distance of 32, right? So if I want to go from uppercase to lowercase, I can do 65 plus 32 will give me 97, and that actually works out across the board for everything else. 66 plus 32 gets me to 98, or lowercase b. Or conversely, if you have a lowercase a, and its value is 97, subtract 32, and boom, you have capital A. So, all right, there's some arithmetic here involved, but now that we know that strings are just arrays, and we know that characters, which are in those arrays, are just binary representations of numbers, I think we can manipulate a few of these things as follows. Let me go back to my program here and first ask the question, if the current character in the array during this loop is lowercase, let's force it to uppercase. So how am I going to do that? If the character at s bracket I, the current location in the array, is greater than or equal to lowercase a, and s bracket I is less than or equal to lowercase z. Kind of a weird Boolean expression, but completely legitimate. Because in this array s is a whole bunch of characters that the humans typed in, because that's what a string is. Greater than or equal to a might be a little nonsensical, because when have you ever compared numbers to letters? But we know from week 0, lowercase a is 97. Lowercase z is, what is it, 1? I don't even remember. What is that? 132, we know. And so that would allow us to answer the question, is the current letter lowercase? All right, so let me go ahead here and answer that question. If it is, what do I want to print out? I don't want to print out the letter itself. I want to print out the letter minus 32, right? Because if it happens to be a lowercase a, 97, 97 minus 32 gives me 65, which is uppercase a. And I know that just from having stared at that chart in the past. Else, if the character is not between little a and big A, I'm just going to print out the character itself by printing s bracket I. And at the very end of this, I'm going to go ahead and print out a new line just to move the cursor to the next line. So again, it's a little wordy, but this loop here, which I borrowed from our code previously, just iterates over the string, aka array, character by character, through its length. This line 11 here is just asking the question if that current character, the ith character of s, is greater than or equal to little a and less than or equal to little z, that is between 97 and 132, then we're going to go ahead and force it to uppercase instead. All right, and let me go ahead and zoom out here for just a second. And sorry, I misspoke. 122, which is what you might have said. There's only 26 letters. So 122 is little z. Let me go ahead now and compile and run this program. So make uppercase, /uppercase, and let me type in hi in lowercase, and there's the capitalized version thereof. Let me do it again with like my own name in lowercase, and now it's capitalized as well. Well, what could we do to improve this? Well, you know what? Let's stop reinventing wheels. Let's go to the manual pages. So let me go here and search for something like, I don't know, lowercase, and there I go. I did some autocomplete here. Our little search box is saying that, OK, there's an isLower function. Check whether a character is lowercase. Well, how do I use this? Well, let me check isLower. Now I see the actual man page for this function. Now we see include ctype.h. So that's the header file I need to include. This is the prototype for isLower. It apparently takes a char as input and returns an int, which is a little weird. I feel like isLower should return true or false. So let's scroll down to the description and return value. It returns, oh, this is interesting, and this is a convention in C. This function returns a non-zero int if C is a lowercase letter, and 0 if C is not a lowercase letter. So it returns non-zero, so like 1, -1, something that's not 0 if C is a lowercase letter, and 0 if it is not a lowercase letter. So how can we use this building block? Let me go back to my code here. Let me add this file, include ctype.h. And down here, let me get rid of this cryptic expression, which was kind of painful to come up with, and just ask this, is lower s bracket I? That should actually work. But why? Well, is lower, again, returns a non-zero value if the letter is lowercase. Well, what does that mean? That means it could return 1, it could return -1, it could return 50 or -50. It's actually not precisely defined. Why? Just because. Like, this was a common convention to use 0 to represent false and use any other value to represent true. And so it turns out that inside of Boolean expressions, if you put a value, like a function call like this, that returns 0, that's going to be equivalent to false. It's like the answer being no, it is not lower. But you can also just in parentheses put the name of the function and its arguments and not compare it against anything, because we could do something like this. Well, if it's not equal to 0, then it must be lowercase, because that's the definition. If it returns a non-zero value, it's lowercase. But a more succinct way to do that is just a bit more like English. If it is lower, then print out the character minus 32. So this would be the common way of using one of these is functions to check if the answer is true or false. OK, well, we might be done. OK. No, so it's not necessarily 1. It would be incorrect to check for 1 or -1 or anything else. You want to check for the opposite of 0, so not equals 0, or more succinctly, like I did by just putting it into parentheses. Let me see what happens here. So this is great, but some of you might have spotted a better solution to this problem a moment ago when we were on the manual pages searching for things related to lowercase. What might be another building block we can employ here? Based on what's on the screen here. Yeah. So to upper. There's a function that would literally do the uppercasing for me, so I don't have to get into the weeds of like -32 plus 32. I don't have to consult that chart. Someone has solved this problem for me in the past. And let's see if I can actually get back to it. There we go. Let me go ahead now and use this. So instead of doing s bracket I minus 32, let's use a function that someone else wrote and just say to upper s bracket I. And now it's going to do the solution for me. So if I rerun make uppercase and then do slowly dot uppercase, type in hi, now it's working as expected. And honestly, if I read the documentation for to upper by actually going back to its man page or manual page, what you'll see is that it says if it's lowercase, it will return the uppercase version thereof. If it's not lowercase, it's already uppercase, it's punctuation, it will just return the original character, which means thanks to this function, I can actually tighten this up significantly, get rid of all of my conditional there, and just print out the to upper return value and leave it to whoever wrote that function to figure out if something's uppercase or lowercase. All right, questions on these kinds of tricks? Again, it all reduces to like week 0 basics, but we're just building these abstractions on top. Yeah? Yes, unfortunately, no. There is no easy way in C to say, give me everything. That was for historically performance reasons. They want you to be explicit as to what you want to include. In other languages like Python, Java, one of which we'll see later this term, you can say, give me everything. But that actually tends to be best practice, because it can actually slow down execution or compilation of your code. Yeah? Does to upper accommodate special characters like punctuation? Yes. If I read the documentation more pedantically, we would see exactly that. It will properly hand me back an exclamation point, even if I passed it in. So if I do make uppercase here, and let me do dot slash uppercase, hi with an exclamation point, it's going to handle that too, and just pass it through unchanged. Yeah? Really good question, too. No, we do not have access to a function that at least comes with C or comes with CS50's library that will just force the whole thing to uppercase. In C, that's actually easier said than done. In Python, it's trivial. So stay tuned for another language that will let us do exactly that. All right, so what does this leave us with? There's just let's come full circle now to where we began today, where we were talking about those command line arguments. Recall that we talked about RM taking a command line argument, the file you want to delete. We talked about Clang taking command line arguments that, again, modify the behavior of the program. How is it that maybe you and I can start to write programs that actually take command line arguments? Well, here is where I can finally explain why we've been typing int main void for the past week and just asking that you take on faith that it's just the way you do things. Well, by default in C, at least the most recent versions thereof, there's only 2 official ways to write main functions. You might see other formats online, but they're generally not consistent with the current specification. This, again, was sort of the boilerplate for the simplest function we might write last week. And recall that we've been doing this the whole time, void. What that void means for all of the programs I have written thus far and you have written thus far is that none of our programs that we've written take command line arguments. That's what the void there means. It turns out that main is the way you can specify that your program does, in fact, take command line arguments. That is, words after the command in your terminal window. If you want to actually not use getInt or getString, you want the human to be able to say something like, hello, David, and hit Enter, and just print hello, David on the screen. You can use command line arguments, words after the program name on your command line. So we're going to change this in a moment to be something more verbose, but something that's now a bit more familiar syntactically. If you change that void in main to be this incantation instead, int argc, comma, string argv, open bracket, close bracket, you are now giving yourself access to writing programs that take command line arguments. Argc, which stands for argument count, is going to be an integer that stores how many words the human typed at the prompt. The C automatically gives that to you. String argv stands for argument vector. That's going to be an array of all of the words that the human typed at the prompt. So with today's building block of an array, we have the ability now to let the humans type as many words or as few words as they want at the prompt. C is going to automatically put them in an array called argv. And it's going to tell us how many words there are in an int called argc. The int as the return type here we'll come back to in just a moment. Let's actually use now this definition to make maybe just a couple of simple programs, but in problem set 2 will we actually use this to control the behavior of your own code. Let me go ahead and code up a file called argv.0 just to keep it aptly named. Let me go ahead and include CS50.h. Let me go ahead and include, oops, that is not the right name of a program. Let's start that over. Let's go ahead and code up argv.c. And here we have include CS50.h, include standard.io.h, int main not void. Let's actually say int argc string argv open bracket, close bracket. No numbers in between because you don't know in advance how many words the human's going to type at their prompt. Now let's go ahead and do this. Let's write a very simple program that just says, hello, David, hello, Carter, whoever the name is that gets typed, but not using getString. Let's instead have the human just type their name at the prompt, just like rm, just like clang, just like make. So it's just one and done when you hit enter. No additional prompts. Let me go ahead then and do this. Printf, quote unquote, hello, comma, and instead of world today, I want to print out whatever the human typed in. So let's go ahead and do this. Argv bracket 0 for now. But I don't think this is quite what I want, because, of course, that's going to literally print out argv bracket 0 bracket. Then I need a placeholder. So let me put a %s here and then put that here. So if argv is an array, but it's an array of strings, then argv bracket 0 is itself a single string. And so it can be plugged into that %s placeholder. Let me go ahead and save my program. And let me go ahead and compile argv. So far, so good. Let me go ahead now and type in my name after the name of the program. So no getString. I'm literally typing an extra word, my own name, at the prompt. Enter. OK. It's apparently a little buggy in a couple of ways. I forgot my \n, but that's not a huge deal. But apparently, inside of argv is literally everything the humans typed in, including the name of the program. So logically, how do I print out hello David or hello so-and-so and not the actual name of the program? What needs to change here? Yeah. Yeah, so presumably index to 1 if that's the second thing I or whichever human has typed at the prompt. So let's do make argv again, /argv enter. Hello null. So this is another form of null. But this is user error now on my part. I didn't do exactly what I said I would. Yeah. Yeah, I forgot the parameter. So that's actually, I should probably deal with that somehow so that people aren't sort of breaking my program and printing out random things like null. But if I do say argv David, now you see hello David. I can get a little curious, like what's at location 2? Well, we can see make argv bracket /argv David enter. All right, so just nothing is there. But it turns out in a couple weeks, we'll start really poking around memory and see if we can't crash programs deliberately, because nothing is technically stopping me from saying, oh, what's at location 2 million, for instance. We could really start to get curious. But for now, we'll do the right thing. But let's now make sure the human has typed in the right number of words. So let's say this. If argc equals 2, that is the name of the program and one more word after that, go ahead and trust that in argv1, as you proposed, is the person's name. Else, let's go ahead and just default here to something simple and basic, like, well, if we don't get a name from the user, just say hello world, like always. So now we're sort of programming defensively. This time the human, even if they screw up, they don't give us a name or they give us too many names, we're just going to say hello world because I now have some error handling here. Because again, argc is argument count, the number of words total typed at the command line. So make argv /argv. Let me make the same mistake as before. OK, I don't get this weird null behavior. I get something well defined. I could now do David. I could do David Malin, but that's not currently supported. I would need to alter my logic to support more than just 2 words after the prompt. So what's the point of this? At the moment, it's just a simple exercise to actually give myself a way of taking user input when they run the program. Because consider, it's just more convenient in this new command line interface world. If you had to use getString every time you compile your code, it'd be kind of annoying, right? You type make, then you might get a prompt. What would you like to make? then you type in hello or cache or something else, then you hit enter, it just really slows the process. But in this command line interface world, if you support command line arguments, then you can use these little tricks like scrolling up and down in your history with your arrow keys. You can just type commands more quickly because you can do it all at once, and you don't have to keep prompting the user more pedantically for more and more info. So any questions then on command line arguments, which finally reveals why we had void initially, but what more we can now put in main. That's how you take command line arguments. Yeah?
If you were to put, if you were to use argv, and you were to put integers inside of it, would it still give you like a string? Would that still be considered string, or would it be considered like int?
Yes, if you were to type at the command line something like not a word, but something like the number 42, that would actually be treated as a string. Why? Because, again, context matters. So if your program is currently manipulating memory as though it's characters or strings, whatever those patterns of zeros and ones are, they will be interpreted as ASCII text or Unicode text. If we therefore go to the chart here, that might make you wonder, well, then how do you distinguish numbers from letters in the context of something like chars and strings? Well, notice 65 is A, 97 is A, but also 49 is 1, and 50 is 2. So the designers of ASCII and then later Unicode realized, well, wait a minute. If we want to support programs that let you type things that look like numbers, even though they're not technically ints or floats, we need a way in ASCII and Unicode to represent even numbers. So here are your numbers. And it's a little silly that we have numbers representing other numbers. But again, if you're in the world of letters and characters, you got to come up with a mapping for everything. And notice here's the dot. Even if you were to represent 1.23 as a string or as characters, even the dot now is going to be represented as an ASCII character. So again, context here matters. All right, one final example to tease apart what this int is and what it's been doing here for so long. So I'm going to go ahead and add one bit of logic here to a new file that I'm going to call exit.c. So in exit.c, we're going to introduce something that are generally known as exit status. It turns out this is not a feature we've used yet, but it's just useful to know about, especially when automating tests of your own code, when it comes to figuring out if a program succeeded or failed. It turns out that main has one more feature we haven't leveraged, an ability to signal to the user whether something was successful or not. And that's by way of main's return value. So I'm going to go ahead and now modify this program as follows, like this. Suppose I want to write a similar program that requires that the user type a word at the prompt, so that argc has to be 2 for whatever design purpose. If argc does not equal 2, I want to quit out of my program prematurely, because I want to just insist that the user operate the program correctly. So I might give them an error message like missing command line argument \n. But now I want to quit out of the program. Now, how can I do that? The right way, quote unquote, to do that is to return a value from main. Now, it's a little weird because no one called main yet, right? Main just gets called automatically. But the convention is anytime something goes wrong in a program, you should return a non-zero value from main. 1 is fine as a go-to. We don't need to get into the weeds of having many different exit statuses, so to speak. But if you return 1, that is a clue to the system, the Mac, the PC, the cloud device, that something went wrong. Why? Because 1 is not 0. If everything works fine, like let's go ahead and print out hello, comma, %s, like before, quote unquote, argv bracket 1. So this is just a version of the program without an else. So this is the same as doing essentially an else here, like I did earlier. I want to signal to the computer that all is well. And so I return 0. But strictly speaking, if I'm already returning here, I don't technically need, if I really want to be nitpicky, I don't technically need the else, because the only way I'm going to get to line 11 is if I didn't already return. So what's going on here? The only new thing here logically is that for the first time ever, I'm returning a value from main. That's something I could always have done, because main has always been defined by us as taking an int as a return value. by default, main automatically, sort of secretly, returns 0 for you. If you've never once used the return keyword, which you probably haven't in main, it just automatically returns 0, and the system assumes that all went well. But now that we're starting to get a little more sophisticated with our code, and you know, the programmer, something went wrong, you can abort programs early. You can exit out of them by returning some other value besides 0 from main. And this is sort of fortuitous that it's an int, right? 0 means everything worked. Unfortunately, in programming, there are seemingly an infinite number of things that can go wrong. An int gives you 4 billion possible codes that you can use, aka exit statuses, to signify errors. So if you've ever on your Mac or PC gotten some weird pop-up that an error happened, sometimes there's a cryptic number in it. Maybe it's positive, maybe it's negative. It might say error code 123 or negative 49 or something like that. What you're generally seeing are these exit statuses, these return values for main in a program that someone at Microsoft or Apple or somewhere else wrote. Something went wrong. They are sort of unnecessarily showing you, the user, what the error code is, if only so that when you call customer support or submit a ticket, you can tell them what exit status you encountered, what error code you encountered. All right. Any questions then on exit statuses, which is the last of our new building blocks for now? Any questions at all? Yeah? No. The question is, can you do things again and again at the command line like you could with getString and getInt, which by default, recall, are automatically designed to keep prompting the user in their own loop until they give you a int or a float or the like. With command line arguments, no. You're going to get an error message, but then you're going to be returned to your prompt. And it's up to you to type it correctly the next time. Good question. Yeah? If you do not return a value explicitly, main will automatically return 0 for you. Like, that is the way C simply works. So it's not strictly necessary. But now that we're starting to return values explicitly, if something goes wrong, it would be good practice to also start returning a value for main when something goes right and there are no errors, in fact. So let's now get out of the weeds and contextualize this for some actual problems that we'll be solving in the coming days by way of problem set 2 and beyond. So here, for instance, is a problem that you might think back to when you were a kid, the readability of some text or some book, the grade level at which some book is written. If you're a young student, you might read at a first grade level or third grade level in the US. Or if you're in college, presumably you're reading at a university level of text. But what does it mean for text, like in a book or in an essay or something like that, to correspond to some kind of grade level? Well, here's a quote, a title of a childhood book: 1 fish, 2 fish, red fish, blue fish. What might the grade level be for a book that has words like this? Maybe when you were a kid, or if you have siblings still reading these things, what might the grade level of this thing be? Any guesses? Yeah. Sorry, again? Before grade 1 is in fact correct. So that's for really young kids. And why is that? Well, let's consider these are actually pretty simple phrases, right? 1 fish, 2 fish, red. I mean, there's not even verbs in these sentences. They're just nouns and adjectives and very short sentences. And so that might be a heuristic we could use when analyzing text. Well, if the words are kind of short, the sentences are kind of short, everything's very simple, that's probably a very young or early grade level. And so by one formulation, it might indeed be even before grade 1. For someone quite young. How about this? Mr. and Mrs. Dursley of number 4, Privet Drive, were proud to say that they were perfectly normal. Thank you very much. They were the last people you would expect to be involved in anything strange or mysterious because they just didn't hold with such nonsense. And onward. All right, what grade level is this book at? OK, I heard 3rd. 7th, 5th, OK, all over the place. But grade 7, according to one particular measure, and whether or not we can debate exactly what age you were when you read this, and maybe you're feeling ahead of your time or behind now. But here, we have a snippet of text. What makes this text assume an older audience, a more mature audience, a higher grade level, would you think? Yeah. Yeah, it's longer, different types of words. There's commas now and phrases and so forth. So there's just some kind of sophistication to this. So it turns out for the upcoming problem set, among the things you'll do is take as input texts like this and analyze them, considering, well, how many words are in the text? How many sentences are in the text? How many letters are in the text? And use those according to a well-defined formula to prescribe what exactly the grade level of some actual text, there's the third, might actually be. Well, what else are we going to do in the coming days? Well, I've alluded to this notion of cryptography in the past, this notion of scrambling information in such a way that you can hide the contents of a message from someone who might otherwise intercept it, right? The earliest form of this might also be when you're younger and you're in class and you're passing a note from one person to another, from yourself to someone else. You don't want to just necessarily write a note in English or some other written language. You might want to scramble it somehow or encrypt it. Maybe you change the A's to a B and the B's to a C so that if the teacher snaps it up and intercepts it, they can't actually understand what it is you've written because it's encrypted. Now, so long as your friend, the recipient of this note, knows how you manipulated it, how you added or subtracted sort of letters to each other, they can decrypt it, which is to say reverse that process. So formally, in the world of cryptography and computer science, this is just another problem to solve. Your input, though, when you have a message you want to send securely, is what's generally known as plain text. There's some algorithm that's going to then encipher or encrypt that information into what's called ciphertext, which is the scrambled version that theoretically can get safely intercepted, and your message has not been spoiled unless that intercept actually knows what algorithm you used inside of this process. So that would be generally known as a cipher. These ciphers typically take, though, not one input, but two. If, for instance, your cipher is as simple as A becomes B, B becomes C, C becomes D, dot, 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 Z becomes A, you're essentially adding 1 to every letter and encrypting it. Now, that would be what we call the key. You and the recipient both have to agree, presumably before class in advance, what number you're going to use that day to rotate or change all of these letters by. Because when you add 1, they, upon receiving your ciphertext, have to subtract 1 to get back the answer. So for instance, if the input, plain text, is high, as before, and the key is 1, the ciphertext using this simple rotational algorithm, otherwise known as a Caesar cipher, might be IJ exclamation point. So it's similar, but it's at least scrambled at first glance. And unless the teacher really cares to figure out what algorithm are they using today or what key are they using today, it's probably sufficiently secure for your purposes. How do you reverse the process? Well, your friend gets this and reverses it by -1. So I becomes H, J becomes I, and things like punctuation remain untouched, at least in this scheme. So let's consider one final example here. If the input to the algorithm is UIJT XBT DT50, and the key this time is -1, such that now B should become A, and C should become B, and A should become Z. So we're going in the other direction. How might we analyze this? Well, if we spread all the letters out, and we start from left to right, and we start subtracting one letter, U becomes T, I becomes H, J becomes I, T becomes S, X becomes W, A was D, T. This was CS50. We'll see you next time.
All right, so now let's tackle a really big topic, functions. So far in the course, all the programs that we've been writing have been written inside of main. They're pretty simple programs. You don't need to have all these branches and things going on. We can just fit it all inside of main, and it doesn't get terribly overwhelming. But as the course goes on, and as you begin to develop programs independently, they're probably going to start to get a lot more than 10 or 15 lines. You might get to hundreds or thousands or tens of thousands of lines of code, and it's really not that thousands of lines of code. All the programs that we've been writing have been written inside of main. They're pretty simple programs. You don't need to have all these branches and things going on. We can just fit it all inside of main, and it doesn't get terribly overwhelming. But as the course goes on, and as you begin to develop programs independently, they're probably going to start to get a lot more than 10 or 15 lines. You might get to hundreds or thousands or tens of thousands of lines of code, and it's really not that crazy a thought. As such, it's probably not a good idea to keep everything inside of main. It can get a little difficult to find what you're looking for if you do that. Fortunately, though, C and pretty much every other programming language that you might work with allows us to write functions. And I'm just going to take a quick aside here to mention that functions is one area of computer science, and you'll see many more of them at various points throughout the course and if you continue on, where there's a lot of synonyms for the same word. So we call them functions, but you might also hear them referred to as procedures or methods, particularly if you've ever done any object-oriented programming before, and don't worry if you haven't, not a big deal, but in object-oriented languages they're frequently called methods. Sometimes they're called subroutines, but they really all refer to the same basic idea. Let's see what that idea is. What is a function? Well, a function is really nothing more than a black box. A black box that has a set of 0 or more inputs and a single output. So for example, this might be a function. This is a function called func, and it takes 3 inputs, A, B, and C, and inside that black box, we don't know exactly what it does, but it processes the inputs in some way, and it gives us a single output, in this case, Z. Now, to make it a little less abstract, we could say that maybe we have a function called add that takes 3 inputs, A, B, and C, and processes the output in some way inside the black box to produce a single output. So in this case, if add takes 3, 6, and 7, somewhere inside the add function, we would expect them to be added together to produce the output, which is 3 plus 6 plus 7, or 16. Similarly, you have a function called mult that takes 2 inputs, A and B, processes them in some way such that the output of the function is the product of the 2 inputs. The 2 inputs multiplied together. 4 and 5 being passed into mult, something happens, the output we expect is 20. Why do we call it a black box? Well, if we aren't writing the functions ourselves, which we've done quite a bit so far in CS50, we've seen printf, for example, which is a function that we didn't write ourselves, but we do use all the time. If we aren't writing the functions ourselves, we don't really need to know how it's actually implemented under the hood. So for example, the black box I just showed you for multiplication. Mult AB could be defined, and this is just some pseudocode, could be defined as output A times B. That makes sense, right? If we have a function called mult that takes 2 inputs, we would expect that the output would be the 2 inputs multiplied together, A times B. But mult could also be implemented like this. We could have a counter variable that gets set inside of mult to 0, and then we repeat this process B times, add A to counter. So for example, if we multiply 3A by 5B, we could say set counter 0, repeat 5 times, add 3 to counter. So we start at 0, and then we do this 5 times. 3, 6, 9, 12, 15. It's the same result. We still get 3 times 5, just the implementation is different. That's what we mean when we say a black box. It just means we don't really care how it's implemented under the hood as long as the output is what we expect. And in fact, that's part of the contract of using functions, particularly functions that others write. The behavior is always going to be typical and predictable based on the name of the function. And that's why it's really important when you write functions, or when other people write functions that you might use, that those functions have clear, relatively obvious names and are well documented, which is certainly the case for a function like printf. So why do we use functions? Well, as I said earlier, if we write all of our code inside of main, things can get really cumbersome and really complicated. Functions allow us the ability to organize things and break up a very complicated problem into a lot more manageable subparts. Functions also allow us to simplify the coding process. It's a lot easier to debug a 10-line function versus a 100-line function or a 1,000-line function. If we only have to debug small pieces at a time or write small pieces at a time, it makes that programming experience a lot better. Trust me on that one. Lastly, if we write functions, we can reuse those various parts. Functions can be recycled, and they can be used in one program or another. You've already written the function. All you need to do is tell that program where to find that function. We've been recycling and using printf for over 40 years, but it was only written one time. Pretty useful, right? All right, so functions are great. We know that. Now let's start writing them. Let's start getting them into our programs. In order to do that, the first thing we need to do is declare the function. When you declare a function, what you're basically doing is telling the compiler, hey, just so you know, I am going to be writing a function later on, and here's what it's going to look like. The reason for this is because compilers can do some weird things if they see a set of symbols that they're not familiar with. So we just give the compiler a heads up. I'm creating a function, and it's going to do this. Function declarations generally, if you're organizing your code in a way that others will be able to understand and make use of, you generally want to put all of your function declarations at the very top of your code, right before you start writing main even. And conveniently, there's a very standard form that every function declaration follows. They all pretty much look like this. There are 3 parts to a function declaration: return type, name, and argument list. Now, the return type is what kind of variable the function will output. So for example, if we think back a minute ago to the multiplying 2 numbers function, what do we expect if we multiply an integer by an integer? The output will be probably an integer, right? Multiplying 2 integers together, you get an integer. So the return type of that function would be int. Name is what you want to call your function. This is probably the least important part of the function declaration in terms of functionality, but it's actually probably one of the most important parts of the function declaration in terms of knowing what the function actually does. If you name your function f or g or h or mystery or something like that, you're probably going to get a little tripped up trying to remember what those functions do. So it's important to give your functions meaningful names. Lastly, argument list is the comma-separated list of all the inputs to your function, each of which has a type and a name. So not only do you have to specify what type of variable the function will output, you also want to specify what type and types of variables the function will be accepting as inputs. So let's do an example here. Let's just take a look at a more concrete one. So here's an example of a function declaration for a function that would add 2 integers together. The sum of 2 integers is going to be an integer as well, as we just discussed. And so the return type here in green would be int. That just tells us that add 2 ints is going to, at the end of the day, output or spit back out to us an integer. Given what this function does, we want to give it a meaningful name. Add 2 ints seems appropriate considering we're taking 2 integers as inputs and hopefully adding them together. It might be a bit of a cumbersome name, and frankly, this function is probably not necessary since we have the addition operator, if you recall from our discussion of operators previously. But let's just say for the sake of argument that this function is useful, and so we'll call it add 2 ints. Lastly, this function takes 2 inputs, each of which is an integer. So we have this comma-separated list of inputs. Now, we generally want to give a name to each of them so that they can be used within the function. The names aren't terribly important in this case. We don't necessarily have any meaning attached to them, so we can just call them A and B. That's totally fine. If, however, you find yourself in a situation where the names of the variables might actually be important, you might want to call something other than A and B to give them something more symbolically meaningful. But in this case, we don't really know anything else about the function. We just want to add 2 integers, so we'll just call those integers A and B. All right, so that's one example. Why don't you take a second to think about this one? How would we write a function declaration for a function that multiplies 2 floating point numbers? Do you remember what a floating point number is? What would this function declaration look like? I actually recommend that you pause the video here and take, however much time you need, really. Think about what this function declaration would be. What would the return type be? What would the meaningful name be? What would the inputs be? So why don't you pause the video here and write up a function declaration for a function that would multiply 2 floating point numbers together. All right, hopefully you pause the video. So let's take a look at an example of one possible declaration. Float mult 2 reals, float x, float y. The product of two floating point numbers, which recall are how we represent real numbers or numbers with decimal values in C, is going to be a floating point number. When you multiply a decimal by decimal, you're probably going to get a decimal. We want to give a relevant name. Multiply two reals seems fine, but you could really call it multi two floats or multi floats, anything like that, as long as it gave some actual meaning to what this black box was going to do. And again, in this case, we don't seem to have any meaning attached to the names of the variables we're passing in, so we can just call them x and y. Now, if you call them something else, that's totally fine. In fact, if you did this declaration instead using doubles instead of floats, if you recall that doubles are a different way to more precisely specify real numbers or floating point variables, that's totally fine too. Either one of those would be fine. In fact, there are several different combinations of ways to declare this function, but these are two pretty good ones. All right, so we declared a function. That's great. We told the compiler what it is, what we're going to be doing. Now let's actually write that function. Let's give it a definition so that inside the black box, predictable behavior is happening. And in fact, we are multiplying two real numbers together, or adding numbers together, or doing whatever it is that we asked our function to do. So in fact, let's try and define multiply two reals, which we just talked about a second ago. Now, the beginning of a function definition looks almost exactly the same as a function declaration. I have both of them here. At the top is the function declaration. Type, name, comma separated argument list, semicolon. The semicolon indicates that that is a function declaration. The beginning of the function definition looks almost exactly the same. Type, name, comma separated argument list, no semicolon, open curly brace. The open curly brace, just as we've been doing with main, means that we are now beginning to define what happens inside the black box that we've decided to call mult2 reals. Here's one way to implement it. We could declare a new variable of type float called product and assign that variable to the value x times y, and then return product. What does return mean here? Well, return is the way we indicate that's how we're passing the output back out. So return something is the same as this is the output of the black box. So that's how you do it. Here's another way to implement it. We could just return x times y. X is a float, y is a float, so x times y is also a float. We don't even need to create another variable. So that's a different way to implement the exact same black box. Now take a moment, pause the video again, and try and define add two ints, which is the other function we talked about a moment ago. Again, here I put the function declaration, ends with a semicolon, and an open curly brace and a closed curly brace indicate where we will fill in the contents of add two ints, so that we define the predictable behavior inside the black box. So pause the video and take as much time as you need to try and define an implementation of add two ints, such that when the function outputs a value, it does in fact return the sum of the two inputs. So just like the previous example, there are several different ways that you can implement add two ints. Here's one, and here in orange I just had some comments. I just added some comments to indicate what's happening on each line of code. So I declare a variable called sum of type int. I say sum equals a plus b. That's when I'm actually doing the work of adding a and b together, and I return sum. And that makes sense because sum is a variable of type int, right? And what's the data type that this function tells me it's going to output? Int. So I'm returning sum, which is an integer variable, and that makes sense given what we've declared and defined our function to do. Now you can also define the function this way. Int sum equals a plus b. Skip that first step, and then return sum. Now you can also have implemented it this way, which I highly do not recommend. This is bad style for one thing, and really bad design, but it does in fact work. If you take this code, which is in badadder.c, and use it, it actually does add two integers together. It's a very poor implementation of this particular behavior, but it does work. And it's here to illustrate the point that we don't really care what happens inside the black box as long as it has the output that we expect. This is a poorly designed black box, but at the end of the day, it does still output the sum of a plus b. All right, so we've declared functions and we've defined functions, so that's really good. Now let's start to use the functions that we've declared and we've defined. To call a function, it's actually pretty easy. All you need to do is pass it appropriate arguments of the data type that it expects, and then assign the return value of that function, assign the return value of that function to something of the correct type. So let's have a look at this in practice in a file called adder1.c, which I have in my CS50 IDE. So here is adder1.c. At the beginning, you see I have my includes, pound include, standard IO, and CS50.h, and I have my function declaration. This is where I'm telling the compiler I'm going to be writing a function called add two ints. It's going to output an integer type variable. That's what this part is right here. And then I have two inputs to it, a and b, each of which is an integer. Inside of main, I ask the user for input by saying give me an integer, and they are prompted to for getInt, which is a function that is included in the CS50 library, and that gets stored in x, an integer variable. Then we prompt them for another integer. We get another integer and store that in y. And then here on line 28 is where we make our function call. We are saying int z equals add two ints x comma y. Do you see why this makes sense? X is an integer type variable, and y is an integer type variable. So that's good. That makes sense with what our function declaration on line 17 looks like. The comma separated input list expects two integers, a and b. In that case, we can call them whatever we want. It just expects two integers. And x is an integer, and y is an integer. So that works. And we know that function is going to output an integer as well. And so we are storing the output of the function add two ints in an integer type variable, which we're calling z. And then we can say the sum of %i and %i is %i. X, y, and z, respectively, filling in those %i's. What does the definition of add two ints look like? Well, it's pretty simple. It's one of the ones we just saw a second ago. Int sum equals a plus b, return sum. Does this work? Well, let's save the file. And then down here in my terminal, I'm going to make adder1. I'm going to clear my screen. I'm going to zoom in because I know it's a little difficult to see. So we compile this program as adder1, so we can do /adder1. Give me an integer, 10. Give me another integer, 20. The sum of 10 and 20 is 30. So we made a successful function call. Run the function again. -10, 17. The sum of -10 and 17 is 7. This function works. It has the behavior that we expect it to. And so we've made a successful function definition, declaration, and a successful function call. A couple miscellaneous points about functions before we conclude this section. Recall from our discussion of data types previously that functions can sometimes take no inputs. If that's the case, we declare the function as having a void argument list. Do you recall what the most common function we've seen so far that takes a void argument list is? It's main. Recall also that functions sometimes don't actually have an output. In that case, we declare the function as having a void return type. Let's conclude this section by tackling a practice problem. So here's the problem laid out. I want you to write a function called valid triangle. What this function should do is take three real numbers that represent the lengths of the three sides of a triangle as its parameters, or its arguments, or its inputs. Another set of synonyms that you might encounter. Section by tackling a practice problem. Do you recall what the most common function section? Recall from our discussion of data types, we've made a successful function definition, declaration, and a successful function call. A couple miscellaneous points about functions before we conclude this section. Recall from our discussion of data types previously that functions can sometimes take no inputs. If that's the case, we declare the function as having a void argument list. Do you recall what the most common function we've seen so far that takes a void argument list is? It's main. Recall also that functions sometimes don't actually have an output. In that case, we declare the function as having a void return type. Let's conclude this section by tackling a practice problem. So here's the problem laid out. I want you to write a function called valid triangle. What this function should do is take three real numbers that represent the lengths of the three sides of a triangle as its parameters, or its arguments, or its inputs, another set of synonyms that you might encounter. This function should either output true or false, depending on whether those three lengths are capable of making a triangle. Do you remember the data type that we used to indicate true or false? Now, how do you implement this? Well, no, there are a couple of rules regarding triangles that are actually useful to know. A triangle can only have sides with positive length. That makes sense. You're probably saying duh. The other thing to note, though, is that the sum of the lengths of any two sides of the triangle has to be greater than the length of the third side. That's actually true. You can't have a triangle of sides 1, 2, and 4, for example, because 1 plus 2 is not greater than 4. So those are the rules that determine whether or not the three inputs can conceivably form a triangle. So take a couple of minutes and declare and then define this function called valid triangle, such that it actually has the behavior specified here. It will output true if those three sides are capable of comprising a triangle, and false otherwise. Ready to see how you did? Here's one implementation of valid triangle. It's not the only one. Yours might vary slightly, but this one does in fact have the behavior that we expect. We declare our function at the very top, bool valid triangle, float x, float y, float z. So again, this function takes three real numbers as its arguments, floating point value variables, and outputs a true or false value, which is a boolean, recall. So that's why the return type is bool. Then we define the function. First thing we do is check to make sure that all of the sides are positive. If x is less than or equal to 0, or if y is less than or equal to 0, or if z is less than or equal to 0, that can't possibly be a triangle. They don't have positive sides, and so we can return false in that situation. Next, we check to make sure that every pair of inputs is greater than the third one. So if x plus y is less than or equal to z, or if x plus z is less than or equal to y, or if y plus z is less than or equal to x, that also can't be a valid triangle. So we return false again. Assuming we passed both of the checks, though, then we can return true, because those three sides are capable of creating a valid triangle. And that's it. You've now declared and defined, and you may be able to now use and call this function. Great job. I'm Doug Lloyd. This is CS50. As you start working with functions, another thing that's going to become really important to understand, which is the concept of variable scope. So scope is a characteristic of a variable that defines from which functions that variable can be accessed. There are two primary scopes in C, local variables and global variables. Now, local variables can only be accessed within the functions in which they're created. They can't be accessed by every other function that exists in your program, only the function in which it was created. Global variables, on the other hand, can be accessed by any function in the program. And the reason for that is because they're not created inside of any particular function. We declare them outside of all of the functions, which means that every function knows where it is and can access and manipulate it. So far in the course, you've pretty much been working exclusively with local variables. Here's an example of a very, very simple main function and a very simple additional function that we've written. In this case, x, which I colored green just to highlight the locality or the scope of that variable, is local to the function triple. Main cannot refer to x at all. It doesn't know what it is. No other function, in fact, if we had additional functions in here, could refer to x. Similarly, result, which I colored blue, is local only to main. Only main knows what the variable result is. Triple cannot use it. Now, as I mentioned, global variables do exist. If you declare that variable outside of any function, all of the functions in the program can refer to it. So in this case, I've highlighted in green a global. In this case, x, which I colored green just to highlight the locality or the scope of that variable, is local to the function triple. Main cannot refer to x at all. It doesn't know what it is. No other function, in fact, if we had additional functions in here, could refer to x. Similarly, result, which I colored blue, is local only to main. Only main knows what the variable result is. Triple cannot use it. Now, as I mentioned, global variables do exist. If you declare that variable outside of any function, all of the functions in the program can refer to it. So in this case, I've highlighted in green a global variable declaration. In this case, the variable being declared is called global, to be extremely clear about it. It is of type float, and I assign it the value 0.5050. You'll notice that in main and in triple, I am able to refer to global. And in fact, if I go through the program as indicated, main first calls triple, triple multiplies global by 3, which has its value to 1.5 something, 1.51 or something like that. And then main also prints out the value of global. So main will not print out 0.5050, it will print out global times 3, 1.51. So you gotta be careful when you're working with global variables. While they're very flexible in being able to pass information around so that every function can use it, it also can have some dangerous consequences if one function changes the value of a variable before you expect it to be changed. Why does this distinction matter? Why do we care whether some variables are local and others are global? Well, for the most part, local variables in C are what's called passed by value when we make a function call. What does that mean? Well, when a variable is passed by value, the call E, which is another way of saying the function that is receiving the variable that gets passed in as an input, it actually doesn't receive that variable itself. It receives its own copy of it to work with. This is a really important distinction. We just saw a second ago that with global variables, if we manipulate the global variable in one function, its effect is the effect in that one function carries through to every other function. But with local variables, that's not true. Each function, when it receives variables as input, receives copies of those variables, not the variables themselves. So what is the side effect of that? That means that the variable in the caller, the function that is making the function call, is unchanged unless you overwrite it. For example, in this code, foo is not changed at all. In foo equals 4, call triple of foo. Inside of triple, we would expect that foo would be multiplied by 3 in return, but there's actually no effect. Here, though, a very subtle difference. This does have the effect we want. You see why? We're overwriting foo in main this time. So int foo equals 4, foo equals triple foo. When we make that call, triple gets its own copy of foo, its own copy of 4. It says return 4 times 3, or whatever variable gets passed in times 3. And then we assign the return value of triple to foo again. So this actually would overwrite foo. This is the only way to do this with local variables. So now, if we add another line of code here at the end of main to print out the value of foo, it would in fact print out 12. Variable scope is generally not too much of a problem if you name all of your variables different things, but it can get kind of nasty if the same variable name appears in multiple functions, which will happen a lot if you ever do work in the real world where you are working on collaborative programs and people in different teams are working together to write the same program or the same set of programs. They'll frequently reuse variable names, particularly common ones like x, y, I, j, and so on. But when variables have the same name, scope issues can get a little trickier to parse. For example, do you know what will be printed out at the end of this particular program? Take a minute, pause the video, and read through this program. You can see at the top we have a function declaration for a function called increment. That function takes a single parameter, an integer, which we call x, and it outputs an integer. That's the return type at the beginning. Then we have main, a couple of lines of code in main, the last of which is a print statement. And remember, that's the question here. What is actually going to be printed at the end of this function? And then we actually have the definition of increment below. So take a minute, step through the code, trace things out. Do you know what will be printed at the end of this particular program? All right, hopefully you've taken a few seconds to try and parse this one out. Let's do it together. So I crossed out increment declaration at the top there. It was kind of a distraction. It's not its own variable. It doesn't have its own scope. It's just a function declaration. So for purposes of trying to parse out what's happening in this program, we might as well just avoid it. Now, we have in this case, the reason this problem is tricky is because we have local variables in both main and increment, each of which is called x. And of course, the crux of this issue is trying to suss out which x gets changed and how does it get changed. So I've colored every instance of x that's local to main red, and I've colored every instance of x that's local to increment blue. Notice in that third line of main, y equals increment x, that increment is not being passed main's x, or the red x. It's getting passed a copy of it, and it's only going to work with that copy of it, the blue x. If you're mathematically inclined, you might have instead thought of this as x sub m for main and x sub I for increment, but it's the same idea. X sub m, or the red x's in the previous slide, are the variables that are local, is the instance of x rather that is local to main, and x sub I, or the blue variables in the previous slide, are the instances of x that are local to increment. So, were you able to figure out what this function printed at the end? I'm Doug Lloyd, and this is CS50.
Welcome everyone, my name is Carter, and today I'm going to show you my guessing game and how I can use debug50 to help figure out what's wrong with it. So here, I'm trying to write a guessing game that is sort of in the spirit of the elementary school game, where you would guess a number and someone would tell you it's right or wrong, and I called my program guess, so I can run it in the terminal with /guess. Here I go /guess, hit enter, and I have to guess a number. So here I might guess maybe 2, and hit enter, but then I get this flood of messages in the terminal, and I'm wondering, well, what's wrong with this? Why am I getting so many messages here? And to try to figure that out, I can go into my code with code guess.c. And then I can see, well, I'm not entirely sure what might be wrong here. So I need to pause my code at some point. And for that, I can use a breakpoint. So let me go ahead and go to this left side of my guess.c file where I see these red sort of circles pop up. And I can click on one of them to turn it bright red. And at that point, I've set a pause point in my code, and I can use debug50 to go in and actually step through my code and see what's going on in there. So let me go ahead and type debug50 of guess, hit enter. So now that I have my code opened up in debug50, I can see a few different things. I can see that my number variable is currently set to 0, and my guess is currently set to this odd 32,764. But as I go through my code, I'll actually see those numbers sort of fall into place. So if I use this step over button to sort of walk to the next line of my code, I can see that number becomes 5, as I expect it to on line 6. And then as I go to line 8 and step over that, I get prompted for what's my guess. And at that point, I might type, well, 3 again, and I'll hit enter. And then I see guess becomes 3. So now I'm wondering, well, if my guess is wrong and my number is 5, my guess is 3, shouldn't I only get wrong guess just once? So I'll actually just keep walking through my code with step over, and I'll see I'm printing wrong guess, which seems right. And now I should just exit the program. That should be it. But I really see that my line in that yellow highlight is going back up to 10, line 10 there. and it's actually continuing to go through and print wrong guess. And so at this point, I can actually see that maybe the bug in my code is I shouldn't have used a while loop. I should have maybe used an if statement where I'm only checking for this condition once. So now that my while loop has changed to an if statement, I should be able to recompile my code and see what's changed. So I can use make guess, and then I'll run my code, guess. And when I guess 3, I guess I should get wrong guess. So I'll do 3, and then I'll get wrong guess, but also you're correct. And at this point, there's probably another bug in my code. And so I'll actually leave this one up to you to use debug 50 and see, well, why am I getting both wrong guess and you're correct? Welcome, everyone. My name is Carter, and today I'll show you my secret program. You can run the program by typing ./secret into your terminal, and if you type in the right password, you should be able to see come on in. So let's try it out. I'll do ./secret, and maybe I don't know the secret phrase, so I'll just say let me in, and at which point I don't get any response. So let me try it again and do ./secret. Maybe password is the password here, but it's not. And I'll just reveal to you that the password is please. So if I type ./secret and I type in please, I should see come on in. But I don't. And so what's the problem here? Well, maybe I should look into my code and maybe step through it bit by bit. So I'll do code secret.c. And I can see the very top of my code starting with this int main void function. To step through my code, remember we can use debug 50 to set a breakpoint or a place to pause in our code. So I can go to this left side here, find a pale red circle, and turn it into a bright red circle as I click it, and set that pause point, or that break point. Now I can do debug 50 of secret, and then my code should boot up, and I should be able to pause right at that moment I'm asking the user for their secret phrase. Of course, I have to actually step over that line for it to actually run in my program, so I'll then step over, and I can type in my secret phrase of please. OK, so that seems pretty good. I see that phrase becomes please, and correct is currently false, but it should change to true after I do this check phrase function. So I'll step over, check phrase, and I see it's actually still false. And so, of course, if I run past line 13, nothing will happen. I actually won't print come on in. So at this point, debug 50 seems to be not really helping me here, right? I've walked through my entire program, but I haven't seen what went wrong in my code. Well, debug 50 has this option to step into a function, actually dive in and see what's happening underneath that hood of that function. So what I can do is go to debug 50 again and run debug 50 with secret, wait for my code to go to that breakpoint again, and I'll walk through that first piece where I type in my phrase please. But now, instead of stepping over this check phrase function, I actually want to dive into it and see what's going on underneath there. So I'll do step into in debug 50, and then see I'm setting my password to be please. So if I step over line 22, I should see that password becomes please, as it does on this left-hand side. And now when I check for if phrase is password, I should actually be able to return true, because it seems that phrase is the same as password. So I'll step over that and see, well, actually I get to line 29, and this is kind of subtle, but in C you can't compare two strings using two equal signs. You actually use a different function called string compare, or strcmp for short. So to use str compare, I can use strcmp and give it two arguments, phrase and password. And with these two inputs, str compare will tell me, are they exactly equivalent or not? If they are equivalent, strcmp, or str compare, will give me 0 as a value back. So now my code is saying, if these strings are equivalent, and I know they are because str compare is giving me 0, I can go ahead and return true and say that this is the correct password. So with this new code here, I should be able to exit debug 50 and go back to the terminal. And now I can make secret again, run secret, type in my password of please, and now there it is. It says come on in. And with that, we've seen how debug 50 can help us not only step over our code, but dive into functions and see the bugs inside of them.
All right, working with single variables is pretty fun, but what if we want to work with a lot of variables, but we don't want to have a bunch of different names flying around our code? In this case, arrays are going to come in really handy. Arrays are a really fundamental data structure for any programming language that you will use, and they're really, really useful, particularly as we'll see in CS50. We use arrays to hold values of the same data type at contiguous memory locations. That is to say, it's a way that we can group a bunch of integers together in memory or a bunch of characters or floats in memory really close together and work with them without having to give each one its own unique name, which can get cumbersome after a little while. Now, one way to analogize arrays is to think about your local post office for a second. So step away from programming and just close your eyes and visualize in your mind your local post office. Usually, in most post offices, there's a large bank of post office boxes on the wall. An array is a giant block of contiguous memory, the same way that a mail bank in your post office is a large space on the wall of the post office. Arrays have been partitioned into small, identically sized blocks of space, each of which is called an element, in the same way that the wall at the post office has been partitioned into small, identically sized blocks of space, which we call a P.O. box. Each element of the array can store a certain amount of data, just as each post office box is able to hold a certain amount of mail. What can be stored in each element of the array is variables of the same data type, such as int or char. Just like in your post office box, you can only fit things of a similar type, such as letters or small packages. Lastly, we can access each element of the array directly by index number, just as we can access our post office box by knowing its mailbox number. Hopefully that analogy helps you get your head around the idea of arrays by analogizing with something else that you are probably already familiar with. In C, the elements of an array are indexed starting from 0, not from 1, and this is really important. In fact, this is why we in CS50 and why computer scientists frequently will count from 0. It's because of C's array indexing, which always starts at 0. So if an array consists of n elements, the first element of that array is located at index 0, and the last element of the array is located at index n minus 1. Again, if there's n elements in our array, the last index is n minus 1. So if our array has 50 elements, the first element is located at index 0, and the last element is located at index 49. Unfortunately, or fortunately, depending on your perspective, C is very lenient here. It will not prevent you from going out of bounds of your array. You can access the -3th element of your array or the 59th element of your array if your array only has 50 elements. It won't stop you from your program from compiling, but at runtime you might encounter a dreaded segmentation fault if you start to access memory that is outside the bounds of what you asked your program to give you. So do be careful. What does an array declaration look like? How do we code an array into existence like we code any other variable? There are 3 parts to an array declaration: a type, a name, and a size. This is very similar to a variable declaration, which is just a type and a name, the size element being the special case for an array because you're getting a bunch of them at the same time. So the type is what kind of variable you want each element of the array to be. Do you want it to be an array of integers? Then your data type should be int. Do you want it to be an array of doubles or floats? Data type should be double or float. The name is what you want to call your array. What do you want to name this giant bank of integers or floats or chars or doubles or whatever have you? What do you want to call it? Pretty self-explanatory. Lastly, size, which goes inside of square brackets, is how many elements you would like your array to contain. How many integers do you want? How many floats do you want? So for example, int student grades 40. This declares an array called student grades, which consists of 40 integers. Pretty self-explanatory, I hope. Here's another example. Double menu prices 8. This creates an array called menu prices, which consists of room in memory for 8 doubles. If you think of every element of an array of type data type, so for example, if a single element of an array of type int, the same way you would think of any other variable of type int, all the familiar operations that we discussed previously in the operations video will make sense. So here we could declare an array of booleans called truth table, which consists of room for 10 booleans. And then just like we could assign a value to any other variable of type boolean, we could say something like truth table square bracket 2, which is how we indicate which element of the truth table? The third element of the truth table. Because remember, we're counting from 0. So that's how we indicate the third element of the truth table. Truth table 2 equals false. Just like we could declare, or we could assign rather any boolean type variable to be false. We can also use it in conditions. If truth table 7 equals true, which is to say if the 8th element of truth table is true, maybe we want to print a message to the user, printf true. I can also just say truth table 10 equals true, right? Well, I can, but it's pretty dangerous because remember, we have an array of 10 booleans. So the highest index that the compiler has given us is 9. This program will compile, but if something else in memory exists where we would expect truth table 10 to go, we could suffer a segmentation fault. We might get away with it, but in general, pretty dangerous. So what I'm doing here is legal C, but not necessarily the best move. Now, when you declare and initialize an array simultaneously, there's actually a pretty special syntax that you can use to fill up the array with starting values. It can get kind of cumbersome to declare an array of size 100 and then have to say element 0 equals this, element 1 equals this, element 2 equals that. What's the point, right? If it's a small array, you could do something like this. Bool truth table 3 equals open curly brace and then comma separate the list of elements that you want to put in the array. Then close curly brace, semicolon. This creates an array of size 3 called truth table with elements false, true, and true. And in fact, the instantiation syntax I have here is exactly the same as doing the individual element syntax below. These two ways of coding would produce the exact same array. Similarly, we could iterate over all the elements of an array using a loop, which in fact is a very strongly recommended at-home exercise. How do you create an array of 100 integers where every element of the array is its index? So for example, we have an array of 100 integers, and in the first element we want to put 0, in the second element we want to put 1, in the third element we want to put 2, and so on and so on. That's a really good at-home exercise to do that. Here, doesn't look like too much has changed, but notice that in between the square brackets this time, I've actually omitted the number. If you're using this very special instantiation syntax to create an array, you actually don't need to indicate the size of the array beforehand. The compiler is smart enough to know that you actually want an array of size 3 because you put 3 elements to the right of the equal sign. If you put 4, it would have given you a truth table of size 4, and so on and so on. Arrays are not restricted to a single dimension, which is pretty cool. You can actually have as many size specifiers as you wish. So for example, if you want to create a board for the game Battleship, which if you've ever played is a game that's played with pegs on a 10 by 10 grid, you could create an array like this. You could say bool Battleship square bracket 10 close square bracket 10 close square bracket. And then you can choose to interpret this in your mind as a 10 by 10 grid of cells. Now in fact, in memory, it really does just remain a 100 element single dimensional array. And this in fact goes for if you have 3 dimensions or 4 or 5, it really just does become multiply all of the indices or all of the size specifiers together and you just get a one-dimensional array of that size. But in terms of organization and visualization and human perception, it can be a lot easier to work with a grid if you're working on a game like tic-tac-toe or Battleship or something like that. It's a great abstraction instead of having to think about a tic-tac-toe board as a line of 9 squares or a Battleship board as a line of 100 squares. A 10 by 10 grid or 3 by 3 grid is probably a lot more easy to perceive. Now, something really important about arrays. We can treat each individual element of the array as a variable. We saw that earlier when we were assigning the value true to certain booleans or testing them in conditionals. But we can't treat entire arrays themselves as variables. We cannot, for example, assign one array to another array using the assignment operator. It's not legal C. If we want to, for example, what we would be doing in that example would be to copy one array into another. If we want to do that, we actually need to use a loop to copy over each individual element one at a time. I know it's a little time consuming. So for example, if we had this line of code, or these couple lines of code, would this work? Well, no, it wouldn't, right? Because we're trying to assign foo to bar. That's not going to work because it's an array, and we just described that that's not legal C. Instead, if we want to copy the contents of foo into bar, which is what we're trying to do here, we would need a syntax like this. We have a for loop that goes from j is equal to 0 up to 5, and we increment j on every iteration of the loop and assign elements like that. This would result in bar also being 1, 2, 3, 4, 5, but we have to do it this very slow element by element way instead of by just copying the entire array. In other programming languages, more modern ones, you can in fact do this that simple equals syntax, but C, unfortunately, we're not allowed to do that. Now, there's one other thing I want to mention about arrays that can be a little bit tricky the first time that you work with them. We discussed in a video about variable scope that most variables in C, when you call them in functions, are passed by value. Do you remember what it means to pass something by value? It means we're making a copy of the variable that's being passed in. The callee function is receiving the variable, doesn't get the variable itself. It gets its own local copy of it to work with. Arrays, of course, do not follow this rule. Rather, what we call this is passing by reference. The callee actually does receive the array. It does not receive its own local copy of it. And if you think about it, this kind of makes sense. If arrays are really large, it takes so much time and effort to make a copy of an array of 100 or 1,000 or 10,000 elements that it's not worth it for a function to receive a copy of it, do some work with it, and then just kind of be done with the copy. It doesn't need to have it hanging around anymore. Because arrays are so bulky and cumbersome, we just pass them by reference. We just trust that function to don't break anything. So it does actually get the array. It doesn't get its own local copy of it. So what does this mean then when the callee manipulates elements of the array? What happens? For now, we'll gloss over why exactly this happens, why arrays are passed by reference and everything else is passed by value. But I promise you, we will return and give you the answer to this in a later video. Here's one more exercise for you before we wrap up things on arrays. There's a bunch of code here that's not particularly good style. I'll make that caveat. There's no comments in here, which is pretty bad form, but it's only because I want to be able to fit everything on the screen. At the top, you can see that I have two function declarations for set array and set int. Set array apparently takes an array of 4 integers as its input, and set int apparently takes a single integer as its input, but both of them don't have an output. The return type of each one is void. In main, we have a couple of lines of code. We declare an integer variable called a and assign it the value 10. We declare an array of 4 integers called b and assign the elements 0, 1, 2, and 3 respectively. Then we have a call to set int and a call to set array. The definitions of set array and set int are down below at the bottom. And so again, I ask you the question, what gets printed out here at the end of main? There's a printf call. I'm printing out 2 integers. I'm printing out the contents of a and the contents of b square bracket 0. Pause the video here and take a minute. Can you figure out what this function will print at the end? Hopefully, if you recall the distinction between passing by value and passing by reference, this problem wasn't too tricky for you, and the answer you would have found is this. If you're not really sure as to why that's the case, take a second, go back, review what I was just discussing about passing arrays by reference versus passing other variables by value, and hopefully it'll make a little bit more sense. I'm Doug Lloyd, and this is CS50. All right, so let's talk about command line arguments. So far in the course, pretty much all of your programs have probably started like this: int main void. We've been collecting user input if we need it in our program, such as the Mario program, for example, by in-program prompts. We haven't needed to modify the declaration of main because instead, inside of main, we just say, you make a call to get int. How large do you want the pyramid to be? Or you make a call to get float. How much change should I output to the user? There is another way, though. And if we want our users to be able to provide data to our program at runtime instead of while the program is running, a subtle distinction, but sometimes a very useful one, we need a new form of declaring main. We can't use int main void if we want to collect other data at the command line when the user runs their program, hence command line arguments. To collect these command line arguments from the user, change your declaration of main to look like this: int main, open paren, int argc, comma, string argv, square brackets, and then open curly brace. So what does that mean already? Well, we are passing in two parameters or arguments or inputs to main. One, an integer called argc, and the other is what? It's an array of strings, right? We see that square bracket notation. It's an array of strings. It's not an individual string. It's an array of strings. And these two arguments, argc and argv, enable you to know what data the user has provided at the command line and how many things they provided at the command line. Pretty useful things to work with. argc stands for argument count. And you should know, by the way, that you could call argc whatever you wanted, and you can call argv whatever you wanted. These are just conventional names that we use for them: argument count, and as we'll see in a second, argument vector, argv. But you don't have to call them argc and argv if you don't want to. But conventionally, that's what we do. So anyway, argc, the argument count. It's an integer type variable, and so as you might expect, if we have two things that we're going to be finding out, what the user typed and how much stuff the user typed, argc is going to tell us how much stuff the user typed. So it gives you a number of command line arguments the user typed when the program was executed. So if your program is run /greedy, and inside of your greedy program, your main function has the declaration int main, int argc, string argv, square brackets, then argc in that case is 1. Now notice we don't count how many things the user typed after the program name. The program name itself counts as a command line argument. So /greedy, in that case, argc is 1. If the user typed /greedy 1024 CS50 at the command line, argc in that case would be 3. And we know this because the way that the division between the strings is detected is whether there is a space or a tab or something like that between them. So any amount of white space, so-called, between the values typed at the command line indicates how many there are. So /greedy space 1024 space CS50, argc in that case is 3. argv is the argument vector. Vector, by the way, is just another word for an array. And this is an array that stores strings, one string per element, which is the strings that the user actually typed at the command line when the program was executed. Now, as is the case with any array, if you recall from our discussion of arrays, the first element of argv is always going to be found at argv square bracket 0. That's the first index of the argv array. So that will always, and in fact, that will always be the name of the program. Will always be located at argv square bracket 0. The last element of argv is always found at argv square brackets argc minus 1. Do you see why? Remember how many elements exist in this array? Well, we know that. It's argc number of elements. If the user typed 3 things at the command line, argc is 3. But because in C, when we're working with arrays, each element of the array, or rather the indices of the array, start at 0. If we have 3 elements in our array, we have an element at argv0, an element at argv1, and an element at argv2. There is no element at argv3 in an array of size 3. So that's why the last element of argv can always be found at argv square brackets argc minus 1. So let's assume the user executes the greedy program as follows. If they type at the command line /greedy space 1024 space CS50. And for whatever reason, we've already prepared our greedy program to know and work with these command line arguments. We didn't previously when we worked on it for the greedy problem. But let's say we've now modified it so that we do process the command line arguments in some way. In this case, argv0 is /greedy. What's argv1? Well, it's 1024, right? It is 1024, but here's a really important distinction. Do you remember the data type of argv? It stores strings, right? But it looks like 1024 is an integer value. This is a really important distinction and is actually going to become something that you might encounter in later problems. Everything in argv is stored as a string. So argv1's contents are the string 1024, consisting of those 4 characters. It's as if the user typed 1024 as individual letters or characters. It is not the integer 1024. And so you can't directly work with it by saying, int 1000, or rather int x equals argv1 minus 24. Intuitively, you might think of that as, okay, well, it's 1024 minus 24, so x is equal to 1000. But in fact, that's not the case because argv1 is a string, the string 1024. Now, there is a function that can be used to convert strings to integers. I won't spoil it for you now, but I'm sure Zamila will be happy to tell you about it in the walkthrough for a future problem. But you can also find functions that would do this in reference 50. If you go to the reference guide, you can find a function that will make this conversion for you. But again, in the walkthrough for a future problem, Zamila will be happy to tell you what function it is that will convert the string 1024 to the integer 1024. All right, so moving on. We've covered argv0, we've covered argv1. What's in argv2? CS50. That one's probably pretty self-explanatory. What's in argv3? Well, again, we don't really know, right? We have an array of size 3. That's how many elements the user typed at the command line. So if we go to argv3, we're now overstepping the bounds of our array. The compiler will let us do this. There's no intuitive problem with it. But in terms of actually what's going to happen, we don't really know. It depends on what is located at the memory where argv3 would be expected to be. And so we could end up getting away scot-free. More likely than not, particularly when we're working with argv as opposed to any other array that's in our program, we're probably going to suffer a segmentation fault. So again, be sure not to overstep the bounds of your arrays, particularly argv, given its high degree of importance in your programs. I'm Doug Lloyd. This is CS50.